cosm. Whoosh.
Imagine that every night of your life, you gaze upon the face of a friend who invariably turns toward you showing only one side. You know every feature of this face, every wrinkle, every scar, every shadow cast in the evening lamplight. But what lies behind that head? What secrets does that side conceal, the one you have never seen and perhaps never will? This is precisely the relationship that binds humanity and the moon, our nearest cosmic neighbor, our eternal companion, our nocturnal deity that illuminated the path of the first hunters and inspired the first poets. The moon performs its majestic dance around Earth, but this dance obeys a strange and remarkable rule. Our satellite always faces us with the same hemisphere. This phenomenon, called tidal locking or synchronous rotation, means that throughout the entire history of human civilization, from the first cave paintings to the moment you read these words, we have seen only approximately 59% of the lunar surface. The remaining 41% remained hidden, like a forbidden chapter in the book of creation. This invisible side of the moon is not dark, in the literal sense. Sunlight illuminates it as generously as the visible side, and there too exist day and night, dawn and dusk. But to human eyes, this side remained a dark territory of the unknown, a blank spot on the map of the cosmos that teased the imagination of astronomers, science fiction writers, and anyone who ever pondered the mysteries of the universe. Why does the moon hide its second face from us? The answer lies in the gravitational embrace between our planet and its satellite, an embrace that has lasted billions of years and gradually slowed the moon's rotation until the period of its rotation around its own axis coincided perfectly with the period of its revolution around Earth. This is a cosmic waltz, whose choreography was constructed by gravitational forces over epochs when life did not yet exist on Earth, not even in its simplest forms. But what exists there, on that side eternally turned away from the blue planet? What mountains rise above its desert plains? What craters preserve the memory of collisions that occurred when Earth was still cooling after its formation? Are there alien bases there, as mid-20th century writers supposed? Or do there lie hidden keys to understanding the origin of our solar system? This mystery tormented humanity for millennia, but only in recent decades have we finally been able to peek behind the cosmic curtain. What we discovered there proved simultaneously disappointing and thrilling, simple and incredibly complex, familiar and utterly alien. The far side of the moon harbors no aliens or ancient artifacts, but it preserves something far more valuable: keys to understanding the history of our cosmic environment, a chronicle of cataclysms and transformations that shaped the face of the solar system. This is a story about how humanity learned to see the invisible, how we sent our eyes and ears into orbit around another world, how we stepped onto a surface that had been hidden from our species throughout the entire evolution of life on Earth. This is a tale of the triumph of human curiosity over natural limitations, of the scientific method that allows us to expand the boundaries of the knowable, of technologies that transform dreams into reality. The journey toward understanding the far side of the moon is not merely a story about space exploration. It is a metaphor for the very process of knowledge, a reminder that behind every discovery lurk 10 new questions, that the map of reality will never be complete, that the universe is inexhaustible in its diversity and complexity. When we look at the moon hanging in the night sky, we see not merely a ball of rock, but a symbol of all that remains unexplored, all that is yet to be discovered. Prepare to embark on a journey beyond the edge of the visible world, to where lunar dust preserves secrets 4.5 billion years old, where giant basins testify to cosmic catastrophes of unimaginable scale, where silence is absolute, and horizons have never seen the blue glow of Earth. Welcome to the far side of the moon, a place that is simultaneously one of the closest corners of the cosmos to us, and one of the most enigmatic. To understand what hides on the far side of the moon and why it remained a mystery for so long, we must first comprehend celestial mechanics, that elegant mathematics of motion governing the dance of cosmic bodies. The story of tidal locking is a story about gravity's patience, about a force that acts slowly but inexorably, shaping the architecture of planetary systems over billions of years. When the Moon first formed, according to the most widely accepted hypothesis today, as a result of a catastrophic collision between the young Earth and a Mars-sized planetesimal that scientists poetically named Theia after the Titaness from Greek mythology, it rotated around its axis much faster. Imagine a figure skater entering a rapid spin, arms pressed to the body, spinning to create a blur of motion. This is how the young Moon rotated in the sky above primordial Earth, completing a full rotation around its own axis perhaps in a matter of hours. But gravity is a patient sculptor. Earth, being significantly more massive than the Moon, 81 times heavier, to be precise, exerted a powerful tidal influence on its newborn satellite. To understand the essence of tidal forces, imagine stretching an elastic ball. One side experiences stronger attraction than the other, and the ball elongates into an ellipsoidal shape. The same thing happened to the Moon under the influence of Earth's gravity. The Moon is not an absolutely solid body. At the moment of its formation, it was an ocean of molten rock, a glowing fireball in the cosmic void. Later, when its surface cooled and solidified, it still retained a certain plasticity, an ability to deform under external forces. Earth's gravitational field created tidal bulges in the Moon's body, regions where material from the lunar interior slightly rose in the direction toward Earth and in the opposite direction. These tidal bulges are the key to understanding synchronous rotation. When the Moon rotated faster than it orbited around Earth, these bulges could not keep up with the changing direction toward our planet. Friction arose, internal resistance within the Moon's interior that gradually dissipated rotational energy as heat. This can be compared to bicycle brakes. Pads pressing against the wheel convert kinetic energy of motion into thermal energy, slowing the bicycle. In exactly the same way, tidal friction slowed the Moon's rotation. This process proceeded incredibly slowly by human standards. Each century the Moon slowed by fractions of a second. But the cosmos has time in abundance. 1,000,000 years, 10 million, 100 million years passed while the Moon gradually lost the speed of its rotation. Calculations show that the process of tidal locking for the Moon was completed relatively quickly by geological standards, perhaps within the first 10 to 100 million years after its formation. Finally came the moment of equilibrium, a state that physicists call tidal locking or synchronous orbit. The period of the Moon's rotation around its own axis became equal to the period of its revolution around Earth. Both of these periods today comprise approximately 27.3 Earth days. In this state, the tidal bulge on the Moon is always directed exactly at Earth, and there is no longer any displacement that would cause friction. The system achieves stability, a cosmic status quo. This means that when the Moon makes one complete revolution around Earth, it makes exactly one rotation around its axis. Imagine walking in a circle around a chair standing in the center of a room, but always turning to face the chair. During a complete circuit, you will make a full rotation around your own vertical axis, but a person sitting in the chair will always see only your face, never your back. This is exactly how the Moon orbits Earth. But it is important to understand the nuance. The Moon does indeed rotate. The Sun illuminates all parts of its surface as it moves along its orbit. When we observe a new moon, when the Moon is positioned between Earth and the Sun, the far side of the Moon is fully illuminated by daylight, bathing in solar rays. When we see a full moon, when Earth is positioned between the Moon and the Sun, the far side is plunged into lunar night. The term, dark side of the Moon, popularized in culture thanks to Pink Floyd's famous album, is a misnomer. It is more accurate to speak of the far, or hidden, side. Tidal locking is by no means a unique phenomenon in the solar system. It is rather the rule than the exception for planetary satellites. All the large moons of the gas giants, Jupiter's 4 Galilean satellites, Io, Europa, Ganymede, and Callisto, Saturn's largest moon Titan, most moons of Uranus and Neptune, All are tidally locked and turn toward their planets with one side. Even distant Pluto and its moon Charon are mutually tidally locked, constantly facing each other with the same hemispheres, like two dancers frozen in eternal mutual contemplation. Moreover, tidal forces continue to operate today, but now they affect the Earth-Moon system in a different way. The Moon causes tides not only in its own body but also on Earth. We observe this in the rise and fall of ocean waters twice a day. These terrestrial tides are also connected with energy loss through friction, in this case, friction of water against the ocean floor and coastline. As a result, Earth is gradually slowing its rotation, and the Moon is moving away from us. Measurements conducted using laser reflectors left on the Moon by Apollo mission astronauts and Soviet automatic stations show that our satellite is receding from Earth at a rate of approximately 3.8 centimeters per year. This is roughly the same rate at which your fingernails grow. It seems a negligible amount, but if extrapolated over millions and billions of years, the effect becomes dramatic. In the distant past, the Moon was significantly closer to Earth. Immediately after formation, it could have been only 15 to 20,000 kilometers away, appearing in the sky as a gigantic disk occupying a substantial portion of the firmament. And in the distant future? If nothing disrupts the course of events, the Moon will continue to recede until it reaches a distance where Earth itself becomes tidally locked to the Moon. At this moment, both Earth and Moon will be turned toward each other with the same hemispheres. An Earth day will become equal to the lunar month, approximately 50 current Earth days. Of course, this will happen so far in the future, tens of billions of years hence, that the Sun will likely have already transformed into a red giant and consumed both Earth and Moon long before this state is achieved. The phenomenon of tidal locking has profound implications for the habitability of planets. Many exoplanets discovered around other stars orbit very close to their parent stars, so close that they are inevitably tidally locked. This means one hemisphere perpetually faces the star, experiencing eternal day, while the other is plunged into eternal night. On such worlds, there may exist a narrow twilight zone between eternal fire and eternal ice where conditions might be suitable for life. Understanding tidal locking helps us comprehend not only our Moon, but also the potential for life throughout the universe. The Italian astronomer Giovanni Cassini first precisely described the Moon's rotation in the 17th century, though the phenomenon was observed long before him. But it was Sir Isaac Newton, that titan of physics whose laws of motion and universal gravitation revolutionized our understanding of the cosmos, who first explained the physical mechanism behind synchronous rotation. In his monumental work, Philosophiae Naturalis Principia Mathematica, published in 1687, Newton laid the mathematical foundation for understanding tidal forces. The full theory of tidal evolution was developed much later, primarily through the work of George Darwin, son of the famous naturalist Charles Darwin, in the late 19th century. George Darwin, a mathematician and astronomer, conducted detailed calculations showing how tidal friction could have slowed the Moon's rotation and increased the Earth-Moon distance over geological time. His work represented one of the first successful applications of physics to understanding the evolution of celestial systems over immense time scales. Today, we understand that the Moon's tidal locking occurred relatively early in its history, which means that for the vast majority of the Moon's existence, perhaps 4.4 billion of its 4.5 billion years, one hemisphere has never seen Earth rise above its horizon. For that hemisphere, Earth does not exist as a visible celestial object. Instead, it experiences a sky where the sun and stars wheel overhead in their stately procession, where the brilliant points of planets occasionally grace the heavens, but where the large, blue-white marble of Earth never appears. This fundamental asymmetry, one side eternally facing Earth, the other eternally facing away, has profound implications not just for lunar geography but for how we humans have experienced and understood our satellite. For all of recorded history, for all the nights when lovers gazed at the Moon, when sailors navigated by it, when poets composed verses in its honor, when ancient astronomers tracked its movements to create the first calendars, all this time, they saw only one face of that ancient companion. The far side remained a mystery not because of any conspiracy or concealment, but simply because of the clockwork mechanics of celestial motion. It was hidden by the same laws of physics that govern everything from falling apples to orbiting galaxies. To see beyond that horizon, humanity would need to transcend its earthly vantage point, to send eyes into space that could look back and reveal what had always been there, yet always been invisible. Long before humanity possessed the technological capability to observe the far side of the moon, the human imagination had already traveled there countless times. The invisible hemisphere of our celestial companion became a canvas upon which dreamers, writers, and scientists painted their wildest speculations, their deepest fears, and their most audacious hopes about what might exist beyond the reach of human vision. The recognition that we see only one face of the moon dates back to ancient times. The Greek philosopher and mathematician Plutarch, writing in the 1st century of the Common Era, already understood that the moon always shows the same face to Earth. He speculated about what might exist on the other side in his dialogue concerning the face which appears in the orb of the moon, though his speculations were more philosophical than scientific, wondering whether it might harbor different landscapes or perhaps even life. As telescopic astronomy developed following Galileo Galilei's revolutionary observations in 1609, astronomers mapped the near side of the moon with increasing precision. They named its dark plains, Maria, seas, mistakenly believing them to be bodies of water. They catalogued its craters, mountains, and valleys. The moon's visible face became one of the best mapped celestial bodies, second only to Earth itself. But the far side remained stubbornly inaccessible, a blank space in lunar cartography. This blank space on the map naturally attracted speculation. In the 19th century, as astronomy became more sophisticated and the idea of extraterrestrial life gained scientific respectability, some astronomers wondered whether the far side might harbor conditions different from the near side. Perhaps, some speculated, there were vast deposits of water ice, or an atmosphere thick enough to support life, somehow protected from terrestrial observation by its permanent concealment. The birth of science fiction as a literary genre in the late 19th and early 20th centuries brought an explosion of creative speculation about the moon's hidden hemisphere. Jules Verne, in his pioneering work, From the Earth to the Moon, published in 1865, and its sequel, Around the Moon, in 1870, sent his characters on a circumlunar voyage that would have given them views of the far side. Though Verne's astronomy was remarkably accurate for his time, he could only imagine what lay beyond the visible limb. H. G. Wells, in his 1891 novel, The First Men in the Moon, populated the lunar interior with an entire civilization of insectid selenites. While his moon-dwelling aliens lived underground rather than specifically on the far side, his work established a template for imagining the moon as a world that might harbor secrets unknown to terrestrial observers. The far side, by its very inaccessibility, became a natural location for such speculative civilizations. As the 20th century progressed and space travel transitioned from fantasy to plausible future achievement, speculation about the far side intensified. The far side became a staple of pulp science fiction magazines, featured in countless stories as the location of ancient alien bases, Nazi hideouts that survived World War II, mysterious forces affecting Earth's history, or reservoirs of valuable minerals and crystals unknown to terrestrial geology. One particularly persistent notion, which would later influence popular culture significantly, was that the far side might be fundamentally different in composition or appearance from the near side. Some speculated it might be completely smooth, a mirror-like surface reflecting the cosmos. Others imagined it as impossibly rugged, with mountains dwarfing anything on the near side. Still others proposed it might harbor evidence of past lunar volcanic activity, or even signs of a former atmosphere and hydrosphere. The mystique of the far side was enhanced by its absolute inaccessibility to direct observation. Unlike Mars, whose entire surface could eventually be mapped as it rotated, or Venus, whose clouds could at least be observed even if they concealed the surface, the Moon's far side was categorically invisible from Earth. No amount of patience or improvement in telescopes could reveal it. This fundamental limitation made the far side a perfect repository for the unknown, the uncanny, the other. Scientific speculation, as distinct from pure fiction, remained more constrained but was nonetheless influenced by the general cultural fascination. Some astronomers proposed that the far side might have a different crater density, which could provide information about the history of impacts in the inner solar system. Others suggested it might have different geological provinces, offering clues to the Moon's formation and evolution. There were even proposals that the center of the far side might harbor a large basin or feature that could explain subtle irregularities in the Moon's orbit and rotation. The German rocket pioneer Hermann Oberth, one of the founding fathers of rocketry and astronautics, wrote speculatively about lunar exploration in his works from the 1920s and 30s. He understood that photographing the far side would be one of the first major objectives of any space program, as it represented a fundamentally new kind of geographical knowledge, the revelation of a territory that had literally never been seen by human eyes or even human-made instruments. In the Soviet Union, which would ultimately be the first to photograph the far side, scientists and science fiction writers alike dreamed of lunar exploration. The works of Konstantin Tsiolkovsky, the theoretical father of cosmonautics, inspired generations of Soviet engineers and cosmonauts. His technical writings contained careful speculation about what instrumentation would be needed to map the Moon's hidden hemisphere, while his science fiction works imagined human settlements on both sides of the Moon. The isolation of the far side also inspired philosophical reflection. The Moon's far side became a metaphor for the unknown in human experience, for those aspects of reality that remain hidden not because of any active concealment, but simply because of our particular vantage point in the cosmos. It reminded humanity that our perspective is necessarily limited, that there are always regions of reality beyond our immediate perception, and that expanding knowledge requires moving beyond our original position. Some philosophers and scientists pondered whether inhabitants of the far side, if such existed, would have developed a fundamentally different worldview than Earth-based humans. Never having seen Earth in their sky, would they have understood their place in the cosmos differently? Would they have developed astronomy more quickly, unimpaired by the bright object that dominates our night sky? Or would they have faced greater challenges, lacking the inspiration and navigational reference that Earth provided to terrestrial civilizations? The period immediately before the first photographs of the far side were obtained, the middle decades of the 20th century, represented a unique moment in human history. It was a time when we knew enough about the Moon to ask precise scientific questions about its hidden hemisphere, yet lacked the technology to answer them. This gap between question and answer, between knowledge and capability, created a special kind of scientific and cultural tension. Astronomers could observe subtle perturbations in the Moon's motion and use them to deduce certain facts about the far side's mass distribution. They knew, for instance, that the far side could not be dramatically different in density from the near side, or it would affect the Moon's orbit and rotation in detectable ways. They understood that it must be made of the same general types of rock, subject to the same geological processes. But these constraints still left enormous room for specific discoveries. The advent of radio astronomy in the mid-20th century offered tantalizing possibilities. Radio waves could, in principle, bounce off the far side and return information about its surface characteristics. However, the technical challenges were immense, and the resolution of such observations would be poor compared to optical photography. The far side would really only reveal itself when humanity could physically send cameras around the Moon to look back at what had always been hidden. As the space age dawned in 1957 with the launch of Sputnik, the race to be first to photograph the far side became a significant goal in itself, separate from the broader objective of lunar exploration. It represented a symbolic achievement, the revelation of something that had been fundamentally unknowable throughout all of human history up to that moment. In a sense, photographing the far side would expand human knowledge in a uniquely categorical way, not by seeing something familiar in greater detail, but by seeing something that had genuinely never been seen before. The anticipation built through the late 1950s as both the Soviet Union and the United States developed increasingly capable space probes. Each failure of a lunar mission, and there were many, extended the period of uncertainty. Would the far side prove to be radically different, validating the more exotic speculations? Or would it be merely more of the same, more craters, more Maria, more of the familiar lunar landscape? In retrospect, we can see that this period of maximum speculation and minimum knowledge was inevitable for any mystery that depends on technological capability for its resolution. Similar periods attended the first detailed observations of Mars, the first close-up images of Jupiter and Saturn, the first maps of Venus's surface beneath its clouds. In each case, there was a window of time when scientific understanding was sophisticated enough to frame precise questions, but technology was not yet capable of providing definitive answers. The far side of the Moon, however, held a special place in this pantheon of mysteries because of its absolute invisibility from Earth. Mars might be distant and difficult to observe clearly, but at least it could be seen. The far side was categorically beyond reach until the advent of spaceflight. It represented a new kind of discovery, one that required not merely better instruments but a fundamentally new capability, the ability to place those instruments somewhere other than the surface of our home planet. The morning of October 4, 1959, marked a transformative moment in human understanding of the cosmos. On that date, the Soviet automatic interplanetary station Luna 3 successfully completed its photographic mission, capturing the first images ever obtained of the Moon's far side. After 4.5 billion years of existence, after hundreds of millions of years during which life evolved on Earth, after thousands of years of human civilization gazing at the Moon and wondering what lay beyond the visible limb, finally, humanity could see. The achievement was the culmination of intensive Soviet efforts in space exploration that had already yielded spectacular firsts. The first artificial satellite, Sputnik 1, October 1957, the first living creature in orbit, the dog Laika aboard Sputnik 2, November 1957, and the first spacecraft to reach the Moon's surface, Luna 2, September 1959, just weeks before Luna 3's mission. The Soviet space program, under the direction of the legendary but then anonymous chief designer Sergei Pavlovich Korolev, was demonstrating capabilities that seemed to validate the technological and ideological superiority the Soviet leadership claimed. Luna 3 was a remarkable spacecraft for its era, embodying numerous innovative engineering solutions necessitated by the unprecedented nature of its mission. The probe weighed 395 kilograms, about the mass of a large motorcycle, and was shaped somewhat like a cylinder with a conical top, its exterior studded with antennas and sensors. Unlike previous Luna missions, which were essentially high-speed impacts or hard landings, Luna 3 was designed for a specific gravitational trajectory that would carry it around the Moon and back toward Earth, taking photographs during its passage behind the lunar disk. The mission profile itself was a masterpiece of celestial mechanics and mission planning. Luna 3 would approach the Moon, pass behind it from Earth's perspective, photograph the far side while illuminated by the sun, then continue on a trajectory that would bring it back within range of Soviet ground stations for data transmission. The entire sequence required precise timing, flawless execution of maneuvers, and automatic operation during the critical photographic phase when the spacecraft was out of contact with Earth. The camera system aboard Luna 3 represented state-of-the-art space photography for 1959, though by modern standards it seems almost primitive. It consisted of a dual-lens system, one lens with a 200mm focal length for detailed shots, another with a 500mm focal length for higher-resolution images of specific areas. The system used conventional photographic film, actual strips of light-sensitive emulsion, not electronic imaging, which would be automatically developed aboard the spacecraft using an onboard chemical processing system. This onboard film processing system was itself an engineering marvel. In the vacuum and radiation environment of space, with wide temperature swings and no human operator to make adjustments, the spacecraft had to automatically develop the film using chemical baths, fix the images, dry the developed negatives, and then prepare them for electronic scanning. The entire process was choreographed with mechanical timers and sensors, a ballet of automated chemistry performed in the void between worlds. Luna 3 launched from Baikonur Cosmodrome on October 4, 1959, exactly 2 years after Sputnik 1 had opened the space age. The launch vehicle, a modified R-7 ballistic missile, performed flawlessly, sending Luna 3 on its translunar trajectory. As the spacecraft hurtled moonward, Soviet engineers monitored its systems, knowing that the critical photographic session would occur when the probe was behind the moon and therefore out of direct communication. On October 7th, Luna 3 passed within 6,500 kilometers of the lunar surface, close enough for detailed photography, but far enough to avoid the risk of collision with any unexpected mountains or highlands on the unknown far side. As the probe rounded the hidden hemisphere, its orientation system, using optical sensors locked onto the sun and moon, automatically positioned the spacecraft for photography. The shutters clicked, the film advanced, and for the first time in history, cameras captured images of a part of the moon no human eye had ever seen. The photographic session lasted 40 minutes, during which Luna 3 captured 29 images on its film strip. The spacecraft then began the automated development process, converting the latent images into permanent negatives. Once this was complete, Luna 3 continued its trajectory back toward Earth, eventually coming back within range of Soviet ground stations on October 18th. The data transmission system represents another remarkable feat of late 1950s technology. The developed and fixed negatives were scanned by a system similar to early television technology, a moving spot of light traversing the negative, with a photocell measuring the amount of light passing through at each point. This analog electrical signal was then transmitted to Earth via radio waves, where it was reconstructed into images. The process was slow, bandwidth was severely limited, and the resulting images were grainy and low resolution by any standard, but they were unmistakably photographs of a previously unseen world. When Soviet scientists first examined the transmitted images, they must have experienced a complex mixture of triumph, satisfaction, and perhaps a tinge of disappointment. Triumph, certainly, at the successful completion of an extraordinarily difficult mission. Satisfaction at the confirmation of theoretical predictions about the moon's nature. But possibly also disappointment, because the far side, at least in these first crude images, looked remarkably similar to the near side, a heavily cratered surface, battered and ancient, without any obvious signs of the exotic features some had speculated about. The images covered approximately 70% of the far side, showing a continuous vista from near the eastern limb across the center of the hidden hemisphere. Resolution was poor, features smaller than tens of kilometers were indistinct, but the overall character was clear. The far side was indeed lunar, crater upon crater, ranging from small bowls barely visible in the images to large circular features hundreds of kilometers across. There were no obvious large maria like those that dominate the near side's landscape, a fact that would prove scientifically significant. Soviet scientists quickly began the work of creating the first map of the far side, identifying and naming major features. They discovered one particularly large basin, which they named the Sea of Moscow, Mare Moscoviense, and identified a substantial crater that they named Tsiolkovsky, in honor of the theoretical father of cosmonautics. Other features received names commemorating Soviet scientists, cosmonauts, and cultural figures, Lomonosov, Joliot-Curie, Pasteur, and others. The public announcement of the achievement was met with worldwide acclaim and, in the West, with a certain amount of chagrin. The Soviet Union had scored another space spectacular, and Premier Nikita Khrushchev did not hesitate to trumpet the achievement as evidence of socialism's superiority. The images were published in newspapers worldwide, reproduced endlessly despite their poor quality, because they represented something genuinely unprecedented, a new continent, in a sense, added to human geography. Scientists in the West, despite any political complications, recognized the achievement for what it was, a landmark in lunar and planetary science. The International Astronomical Union, the body responsible for planetary nomenclature, officially recognized most of the Soviet names for features on the far side, though the politically charged Sea of Moscow would later be downgraded from a mare to a more modest mare category as higher resolution images showed it to be smaller and less prominent than initially thought. The Luna 3 mission had several unexpected consequences beyond the immediate revelation of the far side's appearance. First, it demonstrated that automated spacecraft could perform complex scientific operations autonomously, without real-time human control. This was a crucial proof of concept for all future deep space exploration, where communication delays make real-time control impossible. The spacecraft had to be smart enough to conduct its mission during the critical period when it was out of contact with Earth. Second, the mission validated the theoretical calculations of lunar gravity and trajectory planning. The fact that Luna 3 successfully executed its figure-8 trajectory around the Moon and back toward Earth demonstrated that Soviet scientists understood lunar orbital mechanics with precision. This knowledge would prove essential for all future lunar missions, both robotic and crewed. Third, the images themselves, despite their limitations, provided the first real data about the far side's geology. The apparent scarcity of large dark maria was immediately noticed and became a subject of scientific investigation. Why would one hemisphere of the Moon be significantly different from the other in this respect? The question would drive research for decades and ultimately lead to important insights about the Moon's thermal history and the mechanics of large impacts. The photographs also showed that the far side appeared to have somewhat higher terrain on average than the near side, an observation later confirmed and refined by subsequent missions. This asymmetry between the two hemispheres, in addition to the difference in Maria distribution, suggested that the Moon's geological evolution had been more complex than a simple uniform process. Luna 3 continued to transmit data as its orbit carried it around Earth, eventually being lost to tracking on April 20, 1960, when it probably re-entered Earth's atmosphere and burned up. The spacecraft had far exceeded its design lifetime, and the data it returned, those grainy, precious photographs, had fulfilled its mission beyond anyone's most optimistic projections. The mission's success inspired intensified efforts by both the Soviet Union and the United States to explore the Moon more thoroughly. The Soviets continued their lunar program with additional photographic missions, each obtaining higher resolution images of the far side. The United States, spurred by President John F. Kennedy's dramatic 1961 commitment to land a man on the Moon before the decade's end, accelerated its own lunar exploration program. In subsequent years, Luna 3's pioneering photographs would be superseded by much better images from other missions, the American Lunar Orbiter Program, the Soviet Zond missions, and eventually the high-resolution photography from Apollo's orbital command modules. But those first images retain a special place in the history of space exploration. They represent a categorical expansion of human knowledge, the revelation of something that had been absolutely unknown for the entire prior history of human civilization. Looking at those grainy, difficult-to-interpret photographs today, knowing what we now know from decades of subsequent observation, it's easy to underestimate their significance. They show, essentially, more of what we already knew existed on the Moon: craters, highlands, and a handful of darker lowlands. But that is precisely the point. Before Luna 3, we didn't know that. We couldn't know it. There was room for speculation that the far side might be fundamentally different, perhaps covered in ice, perhaps harboring a remnant atmosphere, perhaps bearing evidence of recent volcanic activity. Luna 3 closed that door on speculation and opened another on scientific understanding. The far side was revealed to be a place of rock and vacuum, of ancient impacts and frozen time, substantially similar to the near side in its fundamental nature but interestingly different in its details. Those differences, particularly the scarcity of large Maria, would ultimately tell us crucial things about how the Moon formed, how it evolved, and how the Earth-Moon system came to be. The engineers and scientists who built and operated Luna 3 achieved something that can never be repeated. They were the first to see beyond the horizon of human experience, the first to convert what had been categorically unknowable into something known. In doing so, they demonstrated the power of the scientific method and technological capability to expand the boundaries of human knowledge into territory that had seemed permanently beyond reach. The first crude images from Luna 3 whet humanity's appetite for more detailed views of the lunar far side. Over the following decade, a succession of increasingly sophisticated spacecraft would orbit the Moon, each mission adding layers of detail and precision to our understanding of the hidden hemisphere. The transformation from those first fuzzy photographs to comprehensive, high-resolution mapping represents one of the great achievements of the space age. The Soviet Luna program continued with several additional successful photographic missions. Luna 8, 11, 12, 13, and 14 between 1965 and 1968 all carried improved cameras and returned higher quality images of the far side, though none were primary lunar orbiters designed specifically for comprehensive mapping. The Zond program, designed to send spacecraft around the Moon in preparation for crewed missions, also returned excellent photographs including color images of both near and far hemispheres. However, the systematic, comprehensive mapping of the lunar far side would ultimately be achieved by the United States through the Lunar Orbiter Program, one of the most successful planetary exploration programs in the history of space flight. 5 lunar orbiter missions flew between August 1966 and August 1967. And collectively they photographed 99% of the Moon's surface with unprecedented resolution and coverage. The lunar orbiter spacecraft were designed with a specific dual purpose. First, to identify safe landing sites for the upcoming Apollo missions, and second, to advance scientific understanding of the Moon's geology and gravitational field. Each spacecraft carried a sophisticated photographic system based on technology developed for reconnaissance satellites. Indeed, the Lunar Orbiter camera system was derived directly from cameras designed to photograph military installations on Earth from orbit. The heart of each lunar orbiter was its photographic subsystem, which represented remarkable engineering sophistication. Unlike Luna 3's relatively simple system, the Lunar Orbiter camera used a continuous film loop that was photographed, developed, scanned, and transmitted to Earth in an automated cycle. The system could provide resolution as fine as 1 meter under optimal conditions, good enough to see individual boulders on the lunar surface. The film system used a clever technique called velocity over height compensation. As the spacecraft flew over the lunar surface, the camera's optical system moved slightly during each exposure to compensate for the spacecraft's motion, preventing blurring despite the lack of any atmosphere to slow the spacecraft or stabilize its motion. This allowed for long exposures that captured faint details even in shadowed areas, revealing the three-dimensional structure of the landscape through subtle shadow patterns. Each photograph was developed on board using a film processor similar to, but more sophisticated than, the system used on Luna 3. The developed negatives were then scanned by a moving spot of light, and the varying intensity of light passing through the negative was converted to an electrical signal and transmitted to Earth. Ground stations reconstructed these signals into images, with each full-resolution photograph requiring approximately 45 minutes to transmit, a painfully slow process by modern standards, but remarkable for 1960s technology. Lunar Orbiter 1, launched in August 1966, successfully demonstrated the system by photographing potential Apollo landing sites on the near side's equatorial regions. But it also turned its camera toward the far side, capturing medium-resolution images that far surpassed anything previously obtained. Lunar Orbiter 2, launched in November 1966, continued the work, adding more coverage and higher-resolution images. Lunar Orbiter 3, launched in February 1967, provided the first comprehensive photographic coverage of the far side with sufficient resolution to reveal its true nature. For the first time, scientists could see features just a few kilometers across, could trace the walls of craters, could identify different terrain types, and could begin to construct a true geological map. The far side emerged from obscurity into clarity, revealing itself as a deeply scarred, heavily cratered ancient surface. Perhaps the most important discovery from these early comprehensive imaging missions was the confirmation and quantification of the far side's fundamental difference from the near side, the remarkable scarcity of large, dark, smooth Maria. The near side of the Moon is dominated by these features: the Sea of Tranquility, the Sea of Rains, the Ocean of Storms, which make up about 31% of the near side's surface. They are the dark patches visible to the naked eye from Earth, creating the familiar pattern that different cultures have interpreted as a face, a rabbit, or other figures. The far side, in stark contrast, has only about 2% of its surface covered by Maria. The features that do exist, Mare Muscoviense, Mare Ingenii, and a few others, are small by near-side standards. The rest of the far side is ancient, heavily cratered highland terrain, lighter in color and far more densely packed with impact craters of all sizes. This asymmetry was not merely aesthetic, it indicated something profound about the Moon's thermal and geological history. Lunar Orbiter 4, launched in May 1967, was dedicated to high-resolution photographic mapping, capturing detailed images of the entire Moon including comprehensive coverage of the far side. This mission produced the most complete photographic atlas of the lunar surface created before the Apollo era, with enough detail to support not only landing site selection but also serious geological interpretation. Lunar Orbiter 5, the final mission of the series, launched in August 1967, focused on scientifically interesting areas and conducted additional gravitational mapping experiments. By the conclusion of the program, virtually the entire lunar surface had been photographed at medium resolution, with selected areas imaged at very high resolution. The far side was no longer a mystery but a mapped, documented territory ready for scientific investigation. The Lunar Orbiter program's contribution to lunar science cannot be overstated. The photographs revealed not just the general character of the far side but its specific geography. Scientists could now identify distinct geological provinces, trace the relationships between different crater populations, and begin to construct theories about the sequence of events that had shaped the lunar surface over billions of years. One of the most dramatic discoveries was the enormous South Pole Aitken Basin, first recognized in lunar orbiter photographs but not fully appreciated until later missions provided better resolution and more sophisticated analysis techniques. This feature, which we will explore in detail later, is the largest confirmed impact basin in the entire solar system, a scar from a collision so immense it nearly shattered the Moon. The Apollo program, which successfully landed 12 men on the Moon between 1969 and 1972, added another layer of observation to far-side studies, even though all the landing sites were on the near side. This was a practical necessity. The Apollo missions required constant radio communication between the astronauts and mission control, which meant staying on the hemisphere visible from Earth. However, during each Apollo mission's transit to and from the Moon, and during orbital operations, the command module's cameras photographed both hemispheres extensively. Apollo's cameras were superior to those carried by the lunar orbiters, and the astronauts' ability to select targets and adapt to circumstances provided flexibility that robotic missions lacked. The result was thousands of high-quality photographs of the far side, many in color, showing the landscape in vivid detail. The Apollo 8 mission in December 1968, humanity's first voyage to lunar orbit, provided the first human observations of the far side. As the spacecraft rounded the moon and the three astronauts, Frank Borman, Jim Lovell, and Bill Anders, saw the far side directly for the first time, their reaction captured both the wonder and the strangeness of the landscape. The far side appeared dramatically more cratered, more ancient, more thoroughly battered than even the most heavily cratered regions of the near side. Anders described it as a dirty beach, all in grays and whites, without the contrasting dark maria that make the near side's geography visually distinctive. Lovell noted the far side's remarkable uniformity, crater upon crater, with little to distinguish one region from another except size and state of preservation. This monotony was itself scientifically informative. It suggested that the far side's surface dated primarily from the moon's early period of heavy bombardment, before the volcanic eruptions that had filled the near side's basins with dark lava. Subsequent Apollo missions continued the photographic documentation. Apollo 15, 16, and 17, the so-called J missions, with extended scientific capabilities, carried sophisticated cameras and film stocks specifically chosen for geological mapping. The command module pilot on each of these missions conducted extensive photographic surveys while orbiting alone as the other two crew members worked on the surface. Apollo 15's Al Wardens, Apollo 16's Ken Mattingly, and Apollo 17's Ron Evans each spent days photographing the far side in meticulous detail, creating stereo pairs of images that would allow scientists on Earth to construct three-dimensional topographic maps. These photographs remain valuable scientific resources to this day, as the large-format film captured detail that even modern digital systems would have difficulty matching. The Apollo missions also carried instruments to measure the moon's gravitational field, magnetic field, and radiation environment. These measurements, conducted during passes over the far side, revealed unexpected complexity. The gravitational field, in particular, showed significant variations associated with the large impact basins. These gravitational anomalies, called mascons, short for mass concentrations, indicated that dense material lay beneath the surface in these locations, providing clues to the moon's internal structure and the effects of large impacts. By the time the Apollo program concluded in 1972, the far side of the moon had been transformed from an unknown territory into a well-mapped landscape. Scientists possessed thousands of high-quality photographs showing features down to meter-scale resolution in some areas, topographic maps revealing the three-dimensional structure of the surface, and geophysical measurements providing insights into subsurface structure and composition. This wealth of data supported decades of scientific research. Geologists mapped different crater populations, identifying regions of different age and history. They traced rays of material ejected from large impacts, showing how individual events had distributed rock across hundreds or thousands of kilometers. They identified what appeared to be ancient volcanic features, though far less common than on the near side. They began to understand that the far side preserved a more complete record of the moon's early history precisely because it had not been resurfaced by later volcanic activity. The mapping efforts also revealed the far side's generally higher elevation compared to the near side. On average, the far side sits about 1.9 kilometers higher than the near side. This difference is subtle in relative terms, given the moon's 3,474 kilometer diameter, but it is consistent and significant. Combined with the thicker crust on the far side, revealed later by seismic and gravitational studies, this elevation difference provided important constraints on models of the moon's formation and thermal evolution. Perhaps most importantly, the comprehensive mapping showed that while the far side is different from the near side in important ways, it is not alien. It is recognizably the same moon, made of the same materials, shaped by the same types of processes, just at different times and with different intensities. The far side became, through these mapping efforts, not a separate mysterious world but an integral part of our understanding of the moon as a complete, three-dimensional body with a coherent, if complex, geological history. The photographs from lunar orbiter and Apollo missions democratized access to the far side in a way that would have seemed like science fiction just decades earlier. The images were published in atlases and scientific papers, reproduced in textbooks and popular science magazines, and eventually, with the advent of the Internet, made freely available to anyone with a computer. The far side could be explored virtually by school children and amateur astronomers as easily as by professional scientists. This comprehensive mapping set the stage for all future lunar exploration. When later missions, from countries including Japan, China, India, and the United States, returned to lunar orbit, they built upon the foundation established by these pioneering mapping efforts. Each new mission added specific types of data: spectroscopic composition maps, high-resolution topography from laser altimeters, detailed gravitational field measurements, magnetic field maps, and eventually, direct surface exploration by rovers and landers. The transformation from mystery to map territory took less than 2 decades, from Luna 3's first crude photographs in 1959 to the end of the Apollo program in 1972. This represents one of the most rapid expansions of geographical knowledge in human history, an entire hemisphere of a world, completely unknown at the start of the period, thoroughly documented by its end. It stands as testament to what focused scientific effort, supported by adequate resources and driven by both curiosity and competition, can achieve. Stare at a detailed photograph of the lunar far side for any length of time, and one impression dominates above all others. This is a surface that has been relentlessly, systematically, almost obsessively battered. Craters overlap craters which overlap still more craters, creating a palimpsest of destruction written in rock and frozen for billions of years. To understand what lies on the far side of the moon, we must first understand this fundamental characteristic. It is one of the most heavily cratered surfaces in the inner solar system, a museum of cosmic violence that has been preserved in extraordinary detail. Craters, of course, exist on the near side as well. Anyone who looks at the moon through even a modest telescope can see thousands of them. But the far side takes cratering to an almost overwhelming extreme. Crater counts in highland regions of the far side show that the surface is saturated, meaning that new impacts are just as likely to destroy old craters as they are to create fresh ones in previously unimpacted areas. This is the condition of a surface that has been exposed to bombardment for billions of years without any significant resurfacing process to erase the accumulating damage. To understand what we're seeing, we must first understand how impact craters form, a process that involves physics so extreme it seems to belong more to the realm of nuclear weapons than to everyday experience. When a meteoroid, asteroid, or comet fragment strikes the moon at typical cosmic velocities, 10 to 70 kilometers per second, the kinetic energy of the impact exceeds the chemical energy contained in an equivalent mass of TNT by factors of 10 to 100 or more. For a moment at the point of impact, pressures reach millions of atmospheres, temperatures soar to tens of thousands of degrees, and rock behaves more like fluid than solid. The projectile, regardless of whether it's made of stone, metal, or ice, vaporizes almost instantly. The impact site explodes in all directions, excavating a crater many times larger than the impactor itself. The size of the resulting crater depends on the impactor's mass, velocity, and angle of approach, but as a rough rule, the crater will be about 10 to 20 times the diameter of the projectile. A 1-kilometer asteroid striking at 20 kilometers per second will excavate a crater 10 to 20 kilometers across and several kilometers deep. The excavation process is violent and complex. Material immediately beneath the impact point is crushed, melted, or vaporized. Shock waves propagate through the lunar crust, fracturing rock and setting off flows of material that can travel for hundreds of kilometers. For large impacts, the initial crater, called the transient crater, can be significantly deeper and more bowl-shaped than the final form. The crater's floor rebounds upward like a splash frozen in time, and the walls slump inward, creating the final, more shallow structure we observe. The largest impacts create features called basins rather than simple craters. These enormous structures, dozens to thousands of kilometers across, involve such immense energies that they reshape the lunar crust across entire hemispheres. The impact that created the South Pole Aitken Basin, which we will discuss in detail later, excavated material from depths of tens of kilometers, punched through the lunar crust entirely in some places, and distributed debris across thousands of kilometers. Material excavated from the crater is thrown outward in all directions, creating rays, ejecta blankets, and secondary craters where large chunks land with enough force to create their own impacts. Around fresh craters on the Moon, these rays of lighter colored material can extend for distances greater than the crater's diameter, creating the characteristic streak patterns visible in lunar photographs. Over time, these rays darken and fade as micrometeorite bombardment gradually mixes the bright, fresh material with older, space-weathered regolith. The far side's intense cratering tells us several important things about lunar history and about the early solar system more generally. First and most obviously, it tells us that the Moon has been exposed to impact bombardment throughout its history. In the solar system's youth, approximately 4 billion years ago, a period known as the Late Heavy Bombardment subjected the inner solar system to an intense spike in impact rates. The causes of this bombardment period remain debated. It may have been triggered by the migration of the giant planets to their current orbits, which would have disturbed the asteroid belt and the outer solar system, sending a barrage of projectiles sunward. During this era, impacts occurred at rates hundreds or thousands of times higher than today. The Moon, Earth, Mars, Mercury, and Venus all sustained tremendous punishment. On Earth, this record has been erased by plate tectonics, erosion, and billions of years of geological activity. On Mars, partial resurfacing and atmospheric weathering have modified the record. But on the Moon, and particularly on the far side's ancient highlands, the bombardment record has been preserved with remarkable fidelity. By carefully studying crater populations, counting craters of different sizes, measuring their depths and preservation states, and analyzing the relationships between overlapping features, planetary scientists can reconstruct the history of impacts and use this to date different regions of the lunar surface. This technique, called crater counting chronology, has become one of the primary tools for determining the age of surfaces throughout the solar system. The principle is straightforward. Older surfaces accumulate more craters, so counting crater density provides a measure of surface age. By calibrating this technique using radiometric dates from Moon rocks returned by Apollo missions, rocks whose absolute ages can be determined by measuring the decay of radioactive isotopes, scientists have constructed a cratering chronology that can be applied to any rocky body in the inner solar system. This technique reveals that the far side's highlands are among the most ancient surfaces accessible to direct observation anywhere in the solar system, with ages dating back 4.4 to 4.5 billion years, essentially as old as the Moon itself. These surfaces formed shortly after the Moon's magma ocean solidified, creating the primary lunar crust, and they have remained essentially unchanged except for the accumulating record of impacts ever since. The preservation of this ancient surface on the far side, contrasted with its partial obliteration on the near side by volcanic maria, creates one of the Moon's most distinctive asymmetries. Why did volcanic activity largely spare the far side while transforming vast areas of the near side? This question cuts to the heart of understanding the Moon's thermal and geological evolution. The answer involves several interconnected factors. First, the far side's crust is significantly thicker than the near side's, approximately 50 to 60 kilometers on average on the far side compared to 30 to 40 kilometers on the near side. This thicker crust acts as better insulation, preventing heat from the lunar interior from escaping efficiently. Paradoxically, while the near side's thinner crust should have kept the interior hotter, it also provided easier pathways for volcanic magma to reach the surface. Second, large impacts on the near side created basins whose floors lay deep enough to tap into or near the lunar mantle, making it easier for later volcanic eruptions to fill these basins. The impacts fractured the crust extensively, creating weakness zones that volcanic pressure could exploit. The far side, while heavily cratered, lacks the same concentration of very large basins in the size range that would have facilitated extensive later volcanism. Third, there may have been genuine thermal asymmetry in the early Moon, with the near side being slightly hotter than the far side. This could have resulted from the distribution of heat-producing radioactive elements, uranium, thorium, and potassium, which may have been concentrated more on the near side through still debated mechanisms related to the Moon's formation or early magma-ocean differentiation. KREP, a rock type rich in these elements, the acronym stands for K, the chemical symbol for potassium, rare earth elements, and P, phosphorus, is found predominantly in near-side regions and may have acted as a heat source promoting prolonged volcanism. The result of all these factors is that while the near side's large basins filled with lava between roughly 3.9 and 3.1 billion years ago, creating the smooth, dark maria that dominate its appearance, the far side's surface remained largely as it was, a heavily cratered, ancient, frozen record of the Moon's first billion years. Looking at the far side's cratered highlands, we're not seeing random destruction but rather a layered history that can be read like a complex text if we learn the language. Large, degraded craters with softened walls and partially filled floors are the oldest, dating from the Moon's earliest period. Fresher craters with sharp walls, bright rays, and well-defined ejecta blankets are younger, perhaps only millions or even just thousands of years old. The relationships between overlapping craters tell us about the sequence of impacts, which came first, which came later. Some of the far side's craters are enormous, impressive even by solar system standards. Crater Tsiolkovsky, one of the features identified in the first Luna 3 photographs, spans 185 kilometers and is notable for having a dark floor, one of the few places on the far side where volcanic material apparently did manage to reach the surface after the crater's formation. The contrast between its dark floor and bright walls makes it one of the most visually distinctive features on the far side, immediately recognizable in photographs. Crater Korolev, named after Sergei Korolev, the architect of the Soviet space program, measures 437 kilometers across, large enough that its interior contains multiple mountain rings, testimony to the colossal rebound that occurred when the lunar crust sprang back after being compressed by the impact. Crater Jackson, on the far side's limb, spans 71 kilometers and shows beautifully preserved terrace walls, demonstrating the slumping that occurs as freshly excavated crater walls collapse under their own weight. Many far side craters are named after scientists, explorers, and cultural figures from around the world. Crater Pasteur honors the French microbiologist, Crater Joliot-Curie honors the French physicists, Crater Lomonosov honors the Russian polymath. This tradition of international naming reflects both the universal human achievement that lunar exploration represents and the International Astronomical Union's role in assigning official names to features on celestial bodies. The overlapping nature of far side craters creates landscapes that seem almost surreal by terrestrial standards. Imagine standing on the rim of one crater, looking across a floor pocked with dozens of smaller craters, toward distant walls that are themselves disrupted by impacts, with the horizon defined by the rim of yet another larger basin that surrounds the whole complex like a frame within a frame. This is the reality of far side topography. Craters within craters within craters, an endless iteration of circular forms at every scale from meters to hundreds of kilometers. This intense cratering has other effects beyond the obvious topographic consequences. Each impact excavates fresh material from depth, turning over the regolith and bringing up rocks from meters or kilometers below the surface. Each impact also creates heat, melting rock and sometimes creating glass. The cumulative effect of billions of years of this bombardment is a surface layer, the regolith, that is thoroughly mixed, fragmented, and processed. The lunar regolith is not soil in the terrestrial sense. It contains no organic matter, no living organisms, No water except for trace amounts in some permanently shadowed craters. It is instead a mixture of rock fragments, mineral grains, glass beads, and agglutinates, particles fused together by micrometeorite impacts. This material ranges from dust finer than flour to blocks larger than houses, all of it the product of billions of years of impacts large and small. The far side's regolith is thicker on average than the near sides, particularly in the ancient highlands. Measurements suggest depths of 10 to 15 meters are typical, with some locations showing even deeper accumulations. This thick regolith layer has important implications for future exploration and resource utilization. It potentially harbors valuable resources but also presents challenges for drilling, excavation, and construction. Studying the far side's craters also informs our understanding of impact processes throughout the solar system. The physics of cratering is universal. The same processes that created lunar craters also created the enormous impact basins on Mars, the frozen craters on Mercury, and the ancient scars on Earth that have mostly been erased by geological activity. By understanding lunar cratering in detail, we gain insights applicable to planetary surfaces everywhere. The preservation of the far side's cratering record makes it an invaluable natural laboratory. Scientists can test theories about impact mechanics, crater formation, and modification processes using the wealth of examples preserved there. They can calibrate computer models of impact dynamics against real-world results preserved in exquisite detail. They can study how craters of different sizes and ages degrade over time, informing our understanding of space weathering and regolith development. This ancient, battered landscape represents billions of years of cosmic history frozen in stone. Every crater is a moment of violence captured and preserved, a testament to the dynamic, often violent nature of the solar system. The far side of the Moon is not merely cratered, it is a vast archive of impacts, a library of collisions, a museum where every exhibit is a frozen catastrophe waiting to tell its story to anyone patient enough to learn the language written in circles of stone and shadows. If the far side of the Moon is a museum of cosmic violence, then the South Pole Aitken Basin is its centerpiece exhibit, a feature so immense, so ancient, and so scientifically important that it demands separate consideration. Stretching across 2,500 kilometers of the lunar southern hemisphere and extending from the South Pole to the crater Aitken on the far side, this enormous depression is the largest confirmed impact basin on the Moon and one of the largest, oldest, and best preserved impact structures in the entire solar system. To grasp the scale of the South Pole Aitken Basin, consider that its diameter is roughly equivalent to the distance from New York to Los Angeles. If you could stand at its center, the rim would be beyond the horizon in all directions, lost in the distance of the Moon's curved surface. The basin is so large that the curvature of the Moon itself becomes a factor in its geometry. It is not just a crater but a reshaping of an entire hemisphere. The impact that created this colossus must have been one of the most cataclysmic events in the Moon's history, and by extension, one of the most significant collisions in the inner solar system during the late stages of planetary formation. Based on the basin's dimensions and the physics of hypervelocity impacts, scientists estimate that the impactor was likely 150 to 200 kilometers in diameter, an object comparable in size to many asteroids that still exist in the solar system today, or roughly the size of the dwarf planet Ceres. This massive projectile struck the Moon at a velocity probably exceeding 15 kilometers per second, possibly much faster. The kinetic energy released in this collision was staggering, equivalent to billions of times the energy of the largest nuclear weapon ever detonated, comparable to the Chicxulub impact that helped end the age of dinosaurs on Earth, but focused on a body with only 1.2% of Earth's surface area. The explosion would have been visible from Earth, if Earth existed in a form capable of hosting observers, a flash of incandescent fury as an entire hemisphere transformed in seconds. The mechanics of such a titanic impact challenge our intuition. The collision didn't simply dig a hole in the Moon. It created shock waves that propagated through the entire body, temporarily turning solid rock into something that behaved more like a fluid. The initial excavation penetrated deep into the lunar crust and possibly into the mantle itself. Models suggest the impact may have punched through the entire crust in the center of the basin, exposing or at least excavating mantle material and bringing it to the surface where it could be observed and studied billions of years later. The dating of the South Pole Aitken Basin is challenging because no samples have been returned directly from its interior. All the rocks brought back by Apollo missions came from near-side locations, and no mission has yet successfully sampled far-side terrain. However, by analyzing the crater populations superimposed on the basin and comparing them with the cratering chronology calibrated from Apollo samples, scientists have estimated that the South Pole Aitken Basin formed approximately 4.2 to 4.3 billion years ago, during or shortly after the late heavy bombardment. This makes it not only large but also ancient, one of the oldest impact structures we can still clearly recognize. Over the subsequent 4 billion years, the basin has accumulated its own population of craters, creating a complex, multi-layered landscape where ancient basin structures are overprinted with more recent impacts. Yet despite this accumulation of later modifications, the basic structure of the basin remains evident in topographic maps and gravity measurements. The South Pole Aitken Basin's floor lies roughly 8 kilometers lower than the surrounding highlands, an immense depression that makes it by far the lowest region on the Moon. To put this in perspective, if you could drain Earth's oceans and walk across the abyssal plains, the deepest parts would be about 11 kilometers below sea level. The South Pole Aitken Basin, on a body much smaller than Earth, has comparable vertical relief. This depth is remarkable for several reasons. First, it indicates that the impact excavated through most or all of the far side's thick crust. Second, it creates unique conditions for accumulation of materials and volatiles. The basin's floor is cold and shadowed in many areas, particularly near the South Pole where some craters exist in permanent darkness. These permanently shadowed regions have become targets of intense scientific interest because they may harbor water ice and other volatile compounds that have been preserved for billions of years. The composition of the South Pole Aitken Basin's interior, as revealed by remote sensing from orbiting spacecraft, shows distinctive characteristics that support the hypothesis that mantle material was exposed by the impact. Spectroscopic measurements detect enhanced abundances of iron and magnesium-rich minerals compared to typical highlands crust. These minerals, olivine and pyroxene, are characteristic of the lunar mantle, which underlies the anorthositic crust. The presence of mantle materials at the surface is scientifically invaluable. The lunar mantle formed when the Moon's initial magma ocean crystallized, and its composition holds clues to the Moon's bulk composition and thermal history. By studying these materials through remote sensing, and ideally, someday, through direct sampling, scientists can effectively peer into the Moon's interior without having to drill through kilometers of crust. Recent data from China's Chang'e 4 mission, which successfully landed in Von Karman crater within the South Pole Aitken Basin in January 2019, the first soft landing ever achieved on the lunar far side, has provided ground truth for some of these remote sensing observations. The rover U-2 carried instruments to measure the composition and structure of the regolith, and preliminary results confirm enhanced abundances of olivine and pyroxene consistent with mantle derivation. The gravitational signature of the South Pole Aitken Basin, measured precisely by successive lunar orbiting missions, reveals additional complexity. The basin shows a negative gravity anomaly in its center, meaning the gravitational pull is slightly weaker there than would be expected, surrounded by a ring of positive anomalies. This pattern is consistent with a deep depression filled with less dense material, surrounded by denser uplifted mantle rocks. Interestingly, this gravitational pattern differs from that of the near side's large basins, which typically show positive gravity anomalies, mascons, associated with volcanic fill. The South Pole Aitken Basin apparently never experienced the extensive volcanic flooding that characterized Imbrium, Serenitatis, and other near-side basins. This may be because the far side's thicker crust prevented volcanic magma from rising to the surface easily, or because the basin formed early enough that the moon's interior had not yet built up sufficient heat and pressure to drive extensive volcanism. The reason why such an enormous impact didn't trigger massive volcanic flooding is itself an interesting scientific puzzle. Large impacts generate tremendous heat, enough to melt significant volumes of rock, and they fracture the crust deeply, potentially creating pathways for magma to reach the surface. Yet the South Pole Aitken Basin shows only limited volcanic deposits, small patches of dark material that might be impact melt, or might be small volcanic flows, but nothing comparable to the vast maria that flooded Imbrium or Oceanus Procellarum on the near side. One possible explanation involves timing and thermal evolution. If the South Pole Aitken impact occurred early in lunar history, before the moon's interior had heated up sufficiently to generate large volumes of basaltic magma, there simply might not have been enough melt available to flood the basin. Alternatively, the thicker crust on the far side might have prevented magma ascent even if it was present in the mantle below. The debate continues, with researchers using increasingly sophisticated models of lunar thermal evolution to understand the sequence of events. The South Pole Aitken Basin has had profound effects on lunar geology beyond its immediate vicinity. The impact ejected billions of tons of material, distributing it across much of the lunar surface. Rays of ejecta from such a large impact can extend for thousands of kilometers, potentially covering as much as half the moon's surface with a layer of debris. This means that even far from the basin itself, the lunar surface bears the signature of this ancient catastrophe. This widespread ejecta distribution has important implications for interpreting the composition of the lunar surface. Orbital remote sensing detects minerals and rock types across the moon, but distinguishing whether a particular detection represents local bedrock or material transported from elsewhere by impacts becomes challenging. The South Pole Aitken ejecta may be one of the most significant sources of compositional contamination across the lunar far side. The basin's formation may also have had temporary global effects on the moon. The shock of such an enormous impact could have affected the entire body, potentially triggering seismic events, disturbing the thermal structure of the interior, and perhaps even contributing to the evacuation of any residual volatile atmosphere the moon might have possessed shortly after its formation. For a period of time measured perhaps in hours to days, the moon would have been a dramatically different world, a world of incandescent debris clouds, of rock vapor expanding into space, of shock waves reverberating through its interior. From a resource perspective, the South Pole Aitken Basin represents perhaps the most scientifically valuable region on the Moon. A sample return mission from the basin's interior, particularly from locations where mantle material may have been excavated, would provide unprecedented insights into the Moon's interior composition and structure. Such samples would constrain models of the Moon's formation, clarify the nature of the lunar magma ocean and its crystallization sequence, and shed light on the thermal evolution that led to the dichotomy between near and far side volcanism. Additionally, the permanently shadowed craters within and near the basin, particularly those near the South Pole, are now known to harbor water ice deposits. These deposits represent both a scientific treasure, a record of volatile delivery to the inner solar system preserved for billions of years, and a potential resource for future human exploration. Water, which can be broken down into oxygen for breathing and hydrogen for fuel, is the most valuable resource in space. The South Pole Aitken region's combination of scientific importance and potential resources makes it a prime target for future missions. Several nations have expressed interest in exploring the South Pole Aitken Basin in detail. China's Chang'e 4 mission was just the first step. Additional missions are planned to other locations within the basin. NASA has proposed sample return missions and even potential human visits as part of the Artemis program, though these remain in planning stages. India's space agency, ISRO, and other emerging space nations have also indicated interest in lunar far-side exploration. The political and operational challenges of far-side exploration should not be underestimated. Without a direct line of sight to Earth, Missions to the far side require relay satellites to maintain communications. China solved this problem for Chang'e 4 by first deploying the Keiqiao relay satellite to a gravitationally stable location beyond the Moon where it can see both Earth and the far side simultaneously. Future missions will need similar infrastructure, adding cost and complexity. Yet the scientific rewards justify these challenges. The South Pole Aitken Basin is unique in the solar system. We know of no other location where we can so clearly access and study the interior materials of a differentiated rocky body. While larger impact structures exist elsewhere, Hellas Basin on Mars, for instance, or the giant impact basin that covers much of Mercury's northern hemisphere, none combine the South Pole Aitken Basin's size, preservation state, accessibility, and scientific importance. Standing on the floor of the South Pole Aitken Basin, if human explorers ever make that journey, would offer a perspective unlike any other in the solar system. The horizon would curve away in all directions, not to the basin rim, too distant to see, but to smaller craters and ridges that themselves are features of enormous scale. The sun, when visible, would angle low over the landscape, its light never reaching directly down but always sliding in at oblique angles, creating stark contrasts between brilliant highlights and absolute shadow. The Earth would never rise above the horizon, forever beyond the basin's walls. This would be a place of solitude and scientific wonder, the largest excavation in the inner solar system, the Moon's greatest wound, preserved and waiting to tell its story. One of the most striking contrasts between the Moon's near and far hemispheres is immediately obvious even to the most casual observer. The near side is dark and light, marked by the enormous smooth plains of the Maria contrasting with brighter highland regions, while the far side is predominantly uniform in brightness, its surface dominated by ancient, heavily cratered highlands with only scattered small patches of darker material. This asymmetry is not merely aesthetic, it reflects fundamental differences in geological history, crustal structure, and thermal evolution that geologists are still working to fully understand. The Maria, Latin for seas, a name given by early astronomers who believed these dark regions might be bodies of water, are actually vast plains of frozen lava, basaltic rocks that erupted from the lunar interior and flooded low-lying basins over a period from roughly 3.9 to 1.2 billion years ago. The near side contains approximately 17% of the lunar surface covered by these Maria, with some regions like Oceanus Procellarum covering truly enormous areas. Mare Imbrium alone spans roughly 1,100 kilometers across, about the same as the distance from Chicago to New York. In stark contrast, the far side contains only about 2.5% Maria by surface area. The few dark plains that do exist, Mare Muscoviense, Mare Ingenii, and a handful of smaller patches, are modest in size and often lie within large impact basins. This dramatic difference in volcanic resurfacing is the key to understanding why the far side preserves such an ancient, heavily cratered surface while the near side appears relatively smooth in many areas. To understand why this asymmetry exists, we need to delve into the physics and geology of planetary interiors, volcanic processes, and the evolution of the Moon's thermal structure over billions of years. The story begins with the Moon's formation and early differentiation. According to the giant impact hypothesis, now widely accepted as the best explanation for the Moon's origin, our satellite formed from the debris ejected when a Mars-sized object, Theia, collided with the early Earth roughly 4.5 billion years ago. This violent birth left the young Moon completely or almost completely molten, a roiling ocean of liquid rock heated by the enormous energy of the impact and by the subsequent accretion of debris into a coherent body. This magma ocean began to crystallize as it cooled, and because different minerals crystallize at different temperatures and have different densities, the crystallization process led to chemical differentiation. The first minerals to form, olivine and pyroxene, dense iron and magnesium-rich silicates, sank toward the Moon's center, forming what would become the mantle. As crystallization continued, a mineral called plagioclase, lighter than the earlier forming minerals and rich in calcium and aluminum, floated upward, accumulating at the surface to form the primitive crust. This process took perhaps tens of millions of years, eventually producing a moon with an internal structure consisting of a small metallic core, a thick mantle of iron and magnesium-rich silicates, and a crust of plagioclase-rich rock called an orthosite, the material that gives the lunar highlands their characteristically bright appearance. However, this differentiation was not perfectly symmetrical. The final stages of magma ocean crystallization left behind residual melts enriched in elements that don't fit easily into common mineral structures: potassium, K, rare earth elements, Re, and phosphorus, P, collectively known as KREP. These elements, along with uranium, thorium, and other radioactive elements, became concentrated in certain regions, particularly on the near side. This concentration had profound implications for later volcanic activity because radioactive decay is a heat source, and this heat would accumulate preferentially in KREP-rich regions. The early moon was also subject to intense bombardment during the late heavy bombardment period, roughly 4.1 to 3.8 billion years ago. The largest impacts created enormous basins that penetrated deeply into the crust. On the near side, these impacts created potential pathways for later volcanic activity, fractures and weaknesses in the crust that could serve as conduits for rising magma. Following the late heavy bombardment, the moon's interior gradually warmed as radioactive elements in the mantle and lower crust decayed, generating heat. Eventually, temperatures rose high enough in parts of the mantle to begin partial melting, generating basaltic magma, the liquid rock that would eventually erupt onto the surface to form the Maria. But for this magma to reach the surface and create Maria requires overcoming several obstacles. Basaltic magma, while less dense than the mantle rocks from which it forms, is still quite dense compared to the lunar crust. The crust acts as a barrier. Magma rising from the mantle must have enough buoyancy or sufficient pressure from below to push through dozens of kilometers of crustal rock. This is where the difference between near and far side becomes critical. Careful analysis of lunar gravity data and seismic measurements from Apollo instruments, which only covered near-side locations but provided some global constraints, has revealed that the lunar crust is significantly thicker on the far side than on the near side. The near side's crust averages roughly 30 to 40 kilometers thick, while the far side's crust is 50 to 60 kilometers thick on average, with some regions possibly exceeding 70 kilometers. This difference of 20 to 30 kilometers, while only a few % of the moon's diameter, is absolutely crucial for volcanic processes. Imagine trying to push a column of heavy liquid, the magma, up through a 30-kilometer pipe versus a 60-kilometer pipe. The longer the pipe, the more the weight of the magma itself creates back pressure resisting ascent. Only if there's sufficient driving pressure from below, or if the density difference between magma and crustal rock is large enough, will the magma successfully reach the surface. On the near side, the thinner crust and the presence of deep impact basins that had already fractured and thinned the crust further created favorable conditions for volcanic eruptions. Beginning around 3.9 billion years ago and continuing episodically until perhaps 1.2 billion years ago, though most activity ceased by 3 billion years ago, basaltic lavas welled up through fissures and vents, flowing across the floors of impact basins and filling them with layer upon layer of dark volcanic rock. Some individual Maria, like Marimbrium, probably filled through dozens of separate eruptive episodes over hundreds of millions of years. Each eruption added a new layer, creating a stratigraphy that could be read like a history book if we could drill cores through the Maria deposits, which remains a goal for future lunar exploration. On the far side, the story is dramatically different. The thicker crust acted as an effective barrier to volcanic ascent. Even though the far side's mantle presumably underwent similar partial melting and magma generation, there's no reason to think the mantle is fundamentally different between hemispheres. The magma simply couldn't push through the thick crustal barrier in most locations. The driving pressure wasn't sufficient to overcome the weight of 50 to 60 kilometers of overlying rock. Only in a few exceptional circumstances did far-side volcanic rocks reach the surface. Mare Muscoviense, a 445-kilometer-wide patch of dark material in the northern far side, is thought to represent one such exceptional case. It lies within a large impact basin where the impact may have thinned the crust enough to allow volcanic breakthrough. Similarly, Mare Ingenii in the southern far side lies within a basin and may represent another location where impact-related crustal thinning enabled volcanism. Even these far-side maria are different from their near-side counterparts. They're smaller, often don't completely fill their basins, and spectroscopic analysis suggests they may have different compositions, possibly indicating different source regions in the mantle or different degrees of partial melting. The volcanic history of the far side was more limited, more constrained, less vigorous than the near side's exuberant volcanic resurfacing. This brings us to a deeper question. Why is the far side's crust thicker in the first place? This crustal thickness asymmetry is arguably the root cause of the volcanic asymmetry, so understanding its origin is crucial. Several hypotheses have been proposed, and the truth may involve multiple factors operating in combination. One hypothesis involves the temperature difference during magma ocean crystallization. If the near side was somehow hotter than the far side during the final stages of crystallization, perhaps due to tidal heating from Earth when the Moon was much closer, or due to asymmetric distribution of heat-producing radioactive elements, then the magma ocean might have remained liquid longer on the near side. This would allow more time for plagioclase crystals to sink back into the melt rather than accumulating at the surface, resulting in a thinner crust on the near side. Another hypothesis, called the Degree 1 convection model, proposes that convection in the crystallizing magma ocean was asymmetric, with hot material rising preferentially on one side and cool material sinking on the other. This could have led to thicker accumulation of floated plagioclase on one side, the far side, and thinner accumulation on the other, the near side. Computer models have shown this kind of asymmetric convection is possible in certain circumstances, though the specific conditions required remain debated. A third hypothesis invokes the South Pole Aitken Basin. This enormous impact occurred early enough that it might have excavated and removed significant amounts of the near side's original crust through antipodal effects. When a large impact on one side sends shock waves through the body that converge on the opposite side, potentially disrupting the crust there. This could have left the near side with thinner crust. However, timing is crucial for this hypothesis. The South Pole Aitken impact would have to occur after primary crustal formation but before or during the volcanism period. A fourth hypothesis suggests that Earth's presence might have influenced crustal thickness. When the Moon was young and much closer to Earth than it is today, Earth's gravitational field was much stronger at the Moon's location. This could have affected how the magma ocean crystallized, potentially pulling material toward the near side and creating asymmetry in crust thickness. Computer models exploring this possibility have shown it could contribute to the observed asymmetry, though probably not as the sole cause. Recent research has focused on the role of KREP, those incompatible elements that concentrated in the final stages of magma ocean crystallization. There's strong evidence from remote sensing and return samples that KREP is concentrated on the near side, particularly in the region of Oceanus Procellarum and the Imbrium Basin. This near-side KREP concentration had several important effects. First, KREP contains high concentrations of radioactive elements, uranium, thorium, and potassium, which generate heat as they decay. This heat would have made the near side's lower crust and upper mantle hotter over geological time, promoting melting and making it easier for magma to form and rise. Second, KREP-rich rocks have a lower melting point than typical mantle rocks, so they would have begun melting at lower temperatures, potentially providing an additional source of magma on the near side. The combination of thinner crust and enhanced heat production on the near side created a double whammy effect favoring volcanism. Not only was it easier for magma to reach the surface through thinner crust, but there was also more magma being generated in the first place due to the enhanced heating from radioactive decay. The far side, lacking this concentration of KREP, remained cooler and retained its thicker crustal barrier, largely preventing volcanic resurfacing. This volcanic asymmetry has enormous implications for understanding the Moon's surface properties and history. The far side's preservation of ancient highlands means it retains a more complete record of the Moon's first billion years, the period of heavy bombardment, crustal formation, and early evolution. Every crater, every basin, every geological relationship on the far side's highlands is a page in this ancient history book, preserved in remarkable detail because volcanic resurfacing didn't erase it. By contrast, the near side's maria, while beautiful and scientifically valuable in their own right, have obliterated much of the underlying ancient terrain. We can't see what craters or basins existed beneath Mare Tranquillitatis or Oceanus Procellarum before volcanic flooding covered them. This creates an interesting complementarity. The near side teaches us about lunar volcanism and the Moon's thermal evolution from roughly 3.9 to 1.2 billion years ago, while the far side teaches us about the even more ancient period from 4.5 to 3.9 billion years ago. For future exploration and resource utilization, this volcanic asymmetry also matters practically. The near side's maria are relatively smooth, flat, and easy to traverse, ideal landing sites for early missions, which is why Apollo chose maria locations. The far side's rugged, heavily cratered highlands are more challenging for landing and surface operations, though they offer different scientific opportunities and may harbor different resources. The absence of extensive far-side volcanism also means that certain rock types common on the near side are rare or absent on the far side. Basaltic rocks, iron-rich, dark-colored volcanic rocks, are the primary component of maria and are readily accessible on the near side. They're scientifically valuable for understanding the Moon's interior and thermal evolution, and they may also be useful resources for future human activities, as they can be processed to extract oxygen, iron, and other useful elements. On the far side, basaltic rocks are scarce. Instead, the surface is dominated by anorthositic rocks, the bright, aluminum and calcium-rich rocks that make up the primary crust, and by impact breccias, rocks created by the mixing and welding together of different rock types during impacts. This different rock distribution means that mining or resource extraction operations on the far side would work with fundamentally different materials than near side operations. The far side's thicker crust also has implications for what lies beneath. While near side maria basins may have been excavated through the entire crust in places, exposing or nearly exposing mantle rocks, far-side impacts typically didn't penetrate as deeply relative to the total crustal thickness. The South Pole-Aitken Basin is the notable exception. It probably did excavate through the far-side crust to expose mantle materials, which is one reason it's such a high-priority target for future exploration. Understanding the volcanic history of both hemispheres also constrains models of how heat flows through planetary interiors. The Moon, much smaller than Earth, cooled much more rapidly. Small bodies have high surface area to volume ratios, allowing heat to escape efficiently. The fact that lunar volcanism continued episodically until perhaps 1.2 billion years ago, some researchers argue for even younger volcanism based on crater counting, is actually somewhat surprising and suggests that heat generation from radioactive decay was sufficient to drive melting for much longer than initially thought. The cutoff of volcanism, whenever it occurred, marks the point where the Moon's interior finally cooled below the melting point of mantle rocks. Since then, the Moon has been essentially geologically dead. No plate tectonics, no volcanism, no active geological processes except for the steady accumulation of impact craters and the slow working of micrometeorite bombardment that turns rock into regolith. The far side, with its sparse volcanic record, entered this state of geological dormancy much earlier than the near side, making it in some sense the older surface even though both hemispheres formed at the same time. This volcanic asymmetry between near and far sides is unique among solar system bodies we've studied so far. Mars has a hemispheric dichotomy, but it's expressed as a difference in elevation and crustal thickness rather than in volcanic distribution. Mercury shows no obvious hemispheric volcanic asymmetry. Venus, covered in volcanic rocks, shows various regional differences but nothing quite like the Moon's dramatic near/far side contrast. The Moon's situation is special, probably a consequence of its unique formation through a giant impact and its subsequent evolution, while tidally locked to Earth. Solving the mystery of the far side's volcanic absence and understanding the origin of the crustal thickness asymmetry remains an active area of research. Future missions, particularly those that can place seismometers on the far side to study the lunar interior in 3 dimensions, will help constrain these questions. Sample return missions from Farside Highlands and from the rare Farside volcanic deposits would provide crucial ground truth data for testing hypotheses. The mystery is not yet completely solved, but each new mission and each new analysis brings us closer to understanding why the Moon shows such different faces to Earth and to space. Among the most unexpected and scientifically significant discoveries about the far side and the Moon's polar regions is the realization that water ice and other volatile compounds exist in surprising abundance in permanently shadowed craters near both poles, with particularly rich deposits in and around the South Pole Aitken Basin. This discovery has transformed our understanding of the Moon from a completely desiccated world to one that harbors substantial deposits of water, the most valuable resource in space, locked away in cold traps where temperatures haven't risen above 40 Kelvin, -233 degrees Celsius, for billions of years. The story of lunar water is a tale of initial assumptions overturned, of subtle clues gradually noticed, and of remote sensing capabilities improving to the point where they could detect what was long thought impossible. When the Apollo astronauts first returned lunar samples in 1969, the rocks appeared completely dry, drier than any terrestrial rock, drier than meteorites, apparently lacking even trace amounts of water bound into minerals. This observation supported the prevailing theory that the Moon's formation in a giant impact would have volatilized and expelled any water that might have been present. For decades, dry Moon was the operating assumption. Any water mentioned in connection with the Moon was presumed to be either contamination from Earth or hydrogen atoms from the solar wind that had been implanted in surface grains. The idea that significant deposits of water ice might exist on the Moon seemed contrary to all the evidence. The first crack in this certainty came from an unexpected source, the Clementine spacecraft in 1994, which was primarily a military technology demonstrator repurposed for lunar mapping. Data from Clementine's radar experiment suggested that deposits of water ice might exist in permanently shadowed craters near the South Pole. The radar signal was similar to what would be expected from ice deposits, though other explanations were possible, and the scientific community remained cautious. Then in 1998, NASA's Lunar Prospector mission, carrying a neutron spectrometer, detected hydrogen enrichment in regions near both lunar poles. Neutron spectrometry works by measuring how neutrons from cosmic ray interactions with the lunar surface are slowed down and reflected back to space. Hydrogen, being light, is very effective at slowing neutrons, so detecting fewer high-energy neutrons suggests hydrogen presence. The signal was consistent with water ice mixed into the regolith in permanently shadowed polar craters. Still, skepticism remained. Hydrogen could exist in forms other than water ice, perhaps as solar wind implanted hydrogen atoms, perhaps as hydroxyl groups bound to mineral surfaces, perhaps as hydrogen in some unexpected mineral form. Definitive proof would require more sophisticated measurements, and these came from missions in the 2000s. The Chandrayaan-1 mission, launched by India in 2008, carried multiple instruments including NASA's Moon Mineralogy Mapper, M3, which could detect spectroscopic signatures of specific molecules. M3 detected absorption features consistent with water and hydroxyl across much of the Moon's surface, not just at the poles. This discovery was revolutionary. It suggested that water in some form might be much more widespread than anyone had imagined. Additional measurements from the LaCrosse Lunar Crater Observation and Sensing Satellite mission in 2009 provided perhaps the most dramatic confirmation. LaCrosse deliberately crashed its spent Centaur upper stage into Cabeus crater near the South Pole, then flew through the resulting debris plume, analyzing its composition before also impacting the surface. The plume contained not just water but also carbon dioxide, carbon monoxide, ammonia, methane, and other volatiles, a surprisingly rich mixture of compounds, all preserved in the permanent cold of the shadowed crater. Quantifying exactly how much water exists in lunar cold traps has proven challenging. Different techniques and instruments give somewhat different answers, and extrapolating from limited measurements to estimate total deposits involves significant uncertainties. However, current estimates suggest there may be billions of tons of water ice mixed into the regolith of permanently shadowed craters, primarily concentrated near the poles where the geometry of shadows creates the coldest conditions. To understand how water ice can exist on the Moon, we need to understand the physics of cold traps and the Moon's unique thermal environment. The Moon's axis is tilted only about 1.5 degrees relative to its orbital plane, far less than Earth's 23.5-degree tilt. This means that sunlight strikes the lunar poles at extremely shallow angles, always grazing. Near the poles, crater walls and rims cast shadows that, depending on crater location and depth, may never receive direct sunlight. These permanently shadowed regions, PSRs, are among the coldest places in the solar system accessible for exploration. Without sunlight to warm them, and with no atmosphere to transport heat from sunlit areas, these locations have temperatures determined only by radiative heat transfer from surrounding terrain and by minuscule heating from starlight and cosmic background radiation. Measurements indicate temperatures as low as 25 to 40 Kelvin in the coldest PSRs, colder than Pluto's surface, colder than most locations on distant moons of the outer planets. At these temperatures, water ice is extraordinarily stable. It won't sublimate, won't transition directly from solid to gas, even on timescales of billions of years. Any water molecule that happens to land in a PSR will remain trapped there essentially forever unless some event, an impact, a solar flare-driven particle event, an ambitious astronaut with a mining operation, disturbs it. The PSRs are effective cold traps, accumulating and preserving volatiles over geological time. But where does this water come from? The Moon has no appreciable atmosphere, no hydrological cycle, no oceans or lakes or rivers. The water in cold traps must arrive from external sources, and several delivery mechanisms are thought to be important. First, comets occasionally strike the Moon. Comets are often described as dirty snowballs, mixtures of ice and rock from the outer solar system. When a comet impacts the Moon, most of its volatiles are vaporized by the tremendous energy of the collision. However, some fraction of the water molecules from the impact may escape immediate destruction, bouncing across the lunar surface in ballistic hops until they land in a cold trap where they freeze out and become permanently stored. Second, asteroids, particularly certain types that formed in the outer asteroid belt where water ice was stable, may deliver water during impacts. While asteroids are generally rockier and less volatile-rich than comets, some primitive asteroid types contain water bound into minerals or even ice itself. Impact delivery from asteroids, while less dramatic per impact than comets, may be more important overall simply because asteroid impacts are more frequent than comet impacts. Third, and perhaps most interestingly, water may be continuously generated on the Moon itself through chemical reactions driven by solar wind. The solar wind consists primarily of hydrogen ions, protons, streaming outward from the Sun. When these protons strike oxygen-bearing minerals in the lunar regolith, they can combine to form hydroxyl, OH, or water, H2O. This process occurs across the entire lunar surface wherever sunlight and solar wind both reach, creating a thin, transient presence of water that is constantly being formed and constantly being broken down by ultraviolet light and micrometeorite impacts. Most of this solar wind-generated water doesn't last long on the sunlit surface. It's photodissociated, broken apart by light, or sputtered away by particle impacts within hours to days. However, some fraction may migrate toward the poles, bouncing in ballistic trajectories until reaching a cold trap. Over billions of years, even slow accumulation can build up substantial deposits. A fourth potential source involves volcanic outgassing. While the Moon is now geologically inert, during its period of active volcanism billions of years ago, volcanic eruptions would have released gases including water vapor. Most of this would have escaped to space, but again, some fraction might have been cold-trapped in polar regions. This source would have been most important during the period of peak volcanism, roughly 3 to 4 billion years ago. Understanding the origin of lunar water ice is scientifically important because it provides information about volatile delivery to the inner solar system more generally. Earth's water had to come from somewhere. The planet formed too close to the Sun for water ice to have been present in the material that accreted to form our world. Instead, water was likely delivered by impacts from comets and water-rich asteroids after Earth's formation. The Moon's water deposits may preserve a record of this delivery process, frozen in time in the perpetual darkness of polar cold traps. The distribution of water in cold traps is patchy and complex. Not all permanently shadowed craters contain abundant water. Some appear to be ice-poor or ice-free despite being cold enough to retain water. This suggests that simple temperature isn't the only factor. There must be differences in how much water has been delivered to different locations, or differences in how effectively different craters trap incoming volatiles. The form in which the water exists is also variable. In some locations, it may be relatively pure ice, perhaps in layers or lenses within the regolith. In others, it may be intimately mixed with lunar dust at the grain scale, with individual soil particles coated in thin films of ice. The concentration varies from perhaps less than 1% by mass in some locations to possibly 20 to 30% in the coldest, most effectively trapped deposits. The accessibility of this water for future exploration and resource utilization is a topic of intense interest and considerable debate. Extracting water from permanently shadowed craters presents significant challenges. First, you have to work in absolute darkness. Any lights you bring are your only illumination, and managing thermal conditions for equipment and astronauts in these extreme cold environments is difficult. Second, the water is mixed with regolith and must be separated, which requires heating the regolith to release the water, then capturing and purifying the resulting vapor. Despite these challenges, the potential rewards are enormous. Water is the most valuable commodity in space. It can be consumed directly for human needs. Astronauts require several liters per day for drinking, food preparation, and hygiene. It can be electrolyzed to produce oxygen for breathing and hydrogen for fuel, the same chemical reaction that powers some types of fuel cells, but run in reverse. Oxygen and hydrogen together make excellent rocket propellant, and manufacturing propellant on the Moon could dramatically reduce the cost and complexity of space operations by avoiding the need to launch it from Earth's deep gravity well. A water processing facility at the lunar poles could serve as a gas station for spacecraft traveling throughout the inner solar system. Instead of carrying all their propellant from Earth, spacecraft could refuel at the Moon, making missions to Mars, asteroids, or beyond more feasible. This concept of in situ resource utilization, ISRU, has become central to modern space exploration planning. The presence of other volatiles besides water adds additional interest and complexity. Carbon dioxide could be broken down to provide additional oxygen and to create feedstock for manufacturing plastics and other carbon-based materials. Carbon monoxide could be used in chemical processes to synthesize various compounds. Ammonia contains nitrogen, an essential element for life and for manufacturing certain materials. The volatile-rich deposits in polar cold traps are not just water sources but potential chemical factories, raw materials for an emerging space-based economy. Several aspects of lunar polar ice remain poorly understood and are drivers for future exploration. The depth distribution of ice beneath the surface is largely unknown. Does ice exist only in the top few centimeters of regolith? Or does it extend to depths of meters or even tens of meters? The precise composition and isotopic ratios of the ice would reveal its origins. Is it primarily cometary, asteroidal, or solar wind-derived? The age of the deposits is uncertain. Did most of the ice accumulate in the distant past, or is it continuously replenished even today? China's Chang'e series of missions has included polar exploration among its goals, with Chang'e 4 operating in the South Pole Aitken Basin and Chang'e 5 successfully returning samples from a near-polar location on the near side in 2020. Future Chang'e missions are planned to focus specifically on the South Pole, potentially including ice sampling. NASA's Artemis program also targets the lunar South Pole for human landing missions, with water ice as both a scientific objective and a resource utilization goal. Private companies have also expressed interest in lunar polar resources. Several firms are developing technologies for ice prospecting, extraction, and processing, seeing lunar water as a potential business opportunity. While the regulatory and economic framework for such activities remains unclear, international space law is still evolving to address resource utilization. The technical interest is real and growing. The possibility of finding ancient ice that has been frozen in a cold trap for billions of years, raises fascinating scientific possibilities. Such ice would be a time capsule, preserving a record of volatile compounds delivered to the inner solar system over geological time. By analyzing the composition, isotopic ratios, and maybe even trapped gases in ancient ice, scientists could learn about the composition of comets and asteroids from different eras of solar system history, potentially revealing how volatile delivery changed over time. There's even speculation that extremely ancient ice, from the Moon's earliest period, might preserve evidence of conditions in the inner solar system shortly after the Sun and planets formed. Such ice would predate any material we've yet recovered from Earth. Our planet's active geology has recycled or destroyed nearly all rocks older than 4 billion years, and would offer a unique window into the solar system's youth. The far side's connection to these polar ice deposits is significant because the South Pole Aitken Basin, the Moon's largest and most prominent far side feature, extends nearly to the South Pole. Some of the coldest, most persistently shadowed craters lie within or adjacent to this enormous basin. These locations combine two extraordinary features. They lie in the deepest depression on the Moon, excavated by the most powerful impact the Moon likely ever experienced, and they contain some of the most pristine, unaltered material from the early solar system, frozen in cold traps that have been undisturbed for billions of years. From a certain perspective, these polar cold traps represent the antithesis of volcanic maria. Where the maria are products of the Moon's internal heat, melted and erupted from the interior, representing the Moon's attempt to expel heat and differentiate chemically, the cold traps are products of the Moon's external environment, accumulated from space, representing the Moon's role as a passive collector of solar system debris. Together, these contrasting features, hot versus cold, internal versus external, process versus primitive, paint a complete picture of the Moon as a body shaped both by its own evolution and by its environment. Standing at the edge of a permanently shadowed crater near the South Pole, an astronaut would experience a surreal environment. Behind them, sunlight would skim across the lunar highlands at a low angle, creating long shadows and dramatic contrasts. Before them, absolute darkness would fill the crater, a darkness so complete that even after the eyes fully adapted, nothing would be visible without artificial light. The temperature would plummet from perhaps minus 20 degrees Celsius in the sunlight to below minus 230 degrees Celsius in the shadow, a gradient sharper and more extreme than any found naturally on Earth. Yet within that darkness, mixed into the regolith, would lie water, the same substance that fills our oceans, that makes up most of our bodies, that is essential for all life as we know it. Finding it there, preserved in what seems like the least hospitable environment imaginable, reminds us that the universe is full of surprises, that common sense, based on terrestrial experience, often misleads us about how alien environments behave, and that careful observation and measurement reveal wonders we never expected. The lunar ice is not just a scientific curiosity, it is potentially the key that unlocks sustained human presence beyond Earth. With water, we can breathe, drink, grow food, and make fuel. Without it, all these things must be brought from Earth at enormous cost. The recognition that the Moon possesses significant water resources has changed the conversation about lunar exploration from "let's visit" to "let's stay," from "plant a flag" to "build a base." The far side, with its proximity to these resources at the South Pole, has moved from being a distant, inaccessible curiosity to being a destination of central interest for humanity's next great leap into space. Among all the characteristics that make the Moon's far side unique, one stands apart for its implications for future science and exploration. It is the only location in the inner solar system, and potentially one of the few places in the entire solar system, that is perpetually radio quiet, shielded from the cacophony of radio emissions that Earth generates. For radio astronomers dreaming of observations free from interference, the far side represents an unparalleled natural laboratory, a place where the universe's faintest radio whispers might be heard without competition from humanity's constant radio chatter. To appreciate why this matters, we must first understand how thoroughly Earth's radio emissions have come to dominate the local electromagnetic environment. Since Guglielmo Marconi's first radio transmissions in the 1890s, and especially since the explosion of radio, television, radar, and now cellular and satellite communications in the 20th and 21st centuries, Earth has become an increasingly bright radio source. Our planet now radiates across a broad spectrum of radio wavelengths, from long-wave AM radio through shortwave, FM, television broadcasts, GPS signals, satellite communication links, Wi-Fi, cellular networks, and countless other services. This artificial radio noise isn't confined to Earth's surface. Radio waves, being electromagnetic radiation, travel at the speed of light and propagate into space. Some of Earth's radio emissions have now traveled outward for more than a century, creating an expanding bubble of human-generated radio signals that extends more than 100 light-years into the cosmos. From the perspective of a distant observer with sufficiently sensitive equipment, Earth would appear as a remarkably bright radio source, particularly in certain frequency bands, distinctly artificial in character due to the narrow band, often modulated nature of our transmissions. For radio astronomy on Earth's surface, this creates increasing challenges. Radio telescopes must employ sophisticated filtering to separate cosmic signals from terrestrial interference, and even with filtering, certain frequency bands have become essentially unusable for astronomy. Urban areas generate so much radio noise that major observatories must be located in remote regions, far from population centers. Yet even in the most isolated terrestrial locations, satellites passing overhead, aircraft transponders, and the general background hum of modern civilization create constant interference. The Moon's far side offers a radical solution to this problem. Because the Moon is tidally locked to Earth, the far side never has Earth above its horizon. The entire mass of the Moon, approximately 73 quintillion kilograms of rock, blocks virtually all radio emissions from Earth and its satellite constellation. An observatory on the far side would experience radio silence at frequencies where the lunar ionosphere and solar emissions are minimal, creating observing conditions impossible to achieve anywhere on or near Earth. The frequency ranges below 30 MHz are particularly interesting because they cannot be observed from Earth's surface. Our planet's ionosphere reflects these long-wavelength radio waves, preventing them from reaching ground-based telescopes. Space-based observations from Earth orbit are possible but face interference from Earth's radio emissions. The far side is perhaps the only accessible location where these frequencies can be studied with minimal interference, opening a largely unexplored window on the radio universe. What might we observe at these low frequencies? The universe produces radio emissions through various mechanisms. Supernova remnants generate radio waves as their expanding shock fronts accelerate charged particles. Pulsars, rapidly rotating neutron stars, emit beamed radio radiation like cosmic lighthouses. Active galactic nuclei powered by supermassive black holes produce prodigious radio emissions. The cosmic microwave background, the afterglow of the Big Bang itself, has components that extend into radio wavelengths. And perhaps most intriguingly, the neutral hydrogen that filled the universe before the first stars formed should have left a signature at specific radio frequencies that has been shifted by cosmic expansion into the range below 100 MHz. This last observation, detecting the radio signature of the cosmic dark ages, before the first stars ignited, represents one of the holy grails of cosmology. The period between recombination, when the universe became transparent to light approximately 380,000 years after the Big Bang, and the formation of the first stars perhaps 100 million years later, is largely inaccessible to our telescopes. These first stars should have begun ionizing the surrounding neutral hydrogen, creating bubbles of ionized gas that gradually merged and eventually reionized the entire universe. The radio signature of this transition, redshifted to frequencies below 100 MHz, would tell us when and how the first stars formed, answering fundamental questions about cosmic structure formation. Observing this signal requires extraordinary sensitivity and freedom from interference because the expected signal is extremely faint and easily overwhelmed by foreground sources and any terrestrial radio noise. Multiple research groups have attempted these observations from Earth orbit and from ground-based arrays, but results remain tentative and controversial. A radio telescope on the lunar far side, operating in true radio silence, might finally make this historic detection. Beyond specific scientific targets, a far-side radio observatory would simply open new parameter space. History teaches that when we open new observational windows, new wavelength ranges, new sensitivity levels, new angular resolutions, we invariably discover unexpected phenomena. The history of radio astronomy itself illustrates this. Pulsars, quasars, cosmic masers, radio galaxies, the cosmic microwave background, all were discovered serendipitously or found to have properties far different from theoretical predictions. A lunar far side observatory would explore frequency ranges and sensitivity levels largely unexplored, making new discoveries almost certain. Several technical approaches have been proposed for far-side radio astronomy. One concept involves deploying large arrays of simple dipole antennas across the lunar surface, creating interferometric arrays that could map the radio sky with high angular resolution. These antennas could be relatively simple, essentially metal poles or wires laid on or slightly above the surface, but networked together to act as a single enormous telescope spanning kilometers or even hundreds of kilometers. Another approach involves placing radio telescopes in lunar craters, using the crater walls as natural shields against any residual interference and as supports for antenna systems. A crater on the far side could be instrumented with receivers around its rim or on its floor, creating a natural bowl-shaped antenna similar to the Arecibo telescope that operated in Puerto Rico until 2020, but potentially much larger and located in the radio-quiet environment of the far side. More ambitious concepts envision truly enormous arrays spanning hundreds of kilometers, possibly even hemisphere-scale networks that would use the moon's curvature itself as part of the antenna geometry. Such systems would require significant infrastructure, power systems, data processing capabilities, communication relays to get data back to Earth, but would offer unprecedented sensitivity and resolution at low radio frequencies. The logistical challenges of building radio observatories on the far side are substantial but not insurmountable. The basic antenna elements could potentially be relatively simple and lightweight, possibly even manufactured from lunar materials. Cable for interconnecting array elements could be a significant mass challenge, but wireless networking or optical fiber communications might provide alternatives. Power is perhaps the most significant challenge. Solar panels would work during the lunar day, but observatories in permanently shadowed craters would require alternative power sources such as nuclear reactors. Communication from far-side observatories requires relay infrastructure. Since the far side never has direct line of sight to Earth, data must be relayed either through satellites in lunar orbit or around the Moon's limb, or through hardwired connections to relay stations on the near side. China's Keiqiao relay satellite, which enabled the Chang'e 4 mission, demonstrates the orbital relay approach. For long-term far-side operations, multiple relay satellites would provide redundancy and continuous coverage. The radio-quiet environment must also be protected through appropriate spectrum management and operational protocols. There would be little point in establishing far-side observatories if future lunar activities then contaminate the radio environment with transmissions from bases, rovers, and other infrastructure. International agreements similar to those protecting radio-quiet zones on Earth would be needed, designating certain areas of the far side as protected regions where radio emissions are prohibited or strictly limited. Interestingly, the far side's radio silence has implications beyond astronomy. It also makes the location attractive for certain types of fundamental physics experiments that require isolation from electromagnetic interference. Searches for extremely rare particle interactions, tests of gravitational theories, and certain quantum mechanical experiments might benefit from the far side's unique environment. The combination of vacuum, stable thermal conditions, low seismic activity, and radio silence creates a laboratory environment unlike anywhere on Earth. The far side could also serve as a platform for deep space communications and monitoring. Instruments designed to detect and track distant spacecraft, to search for signals from hypothetical extraterrestrial civilizations, SETI, or to monitor the sun and space weather could benefit from the far side location. While these applications would involve transmitting and receiving radio signals, potentially conflicting with passive astronomy, careful frequency and geographic separation could allow multiple uses. Navigation and timekeeping systems might also benefit from far-side installations. Precise atomic clocks on the lunar surface, particularly if networked across multiple locations, could contribute to solar system-wide timekeeping and navigation systems. The Moon's stable orbit and the absence of atmospheric effects make it an attractive platform for such systems, and the far side's isolation from Earth might reduce certain systematic errors. The concept of the far side as pristine scientific real estate raises interesting questions about governance and access. Should the radio-quiet regions of the far side be protected by international treaty, similar to Antarctica's scientific protections? How should competing claims to particularly favorable locations, such as craters ideal for radio telescopes or shadowed regions near the poles with both ice resources and radio-quiet environments, be adjudicated? These questions remain largely unresolved, though discussions within international forums, including the United Nations Committee on the Peaceful Uses of Outer Space, have begun to address them. Some scientists have proposed that the radio-quiet far side should be designated as a scientific preserve, protected from commercial exploitation and unrestricted development. Others argue that economic development and scientific observation can coexist with appropriate management and zoning. The debate parallels discussions on Earth about balancing conservation and development, but with the added complexity that no international legal framework currently exists for lunar resource governance. The value of radio silence may also change over time. As Earth's radio emissions continue to increase and spread across more of the spectrum, the relative advantage of far-side observatories grows. Conversely, if humanity develops quieter technologies or better filtering techniques, the importance of physical shielding might diminish. However, for at least the near to medium-term future, decades to perhaps a century. The far side's natural shielding represents an irreplaceable asset for certain types of observations. Looking toward the far future, some visionaries have proposed even more ambitious concepts. A radio telescope built into the permanently shadowed interior of a polar crater could potentially cool to cryogenic temperatures naturally, creating conditions ideal for ultra-sensitive receivers. A network spanning the entire far side could act as a single coherent telescope with an effective aperture thousands of kilometers across, achieving angular resolution fine enough to image exoplanets or resolve structures in nearby galaxies. These remain speculative, but they illustrate the extraordinary potential of the far side environment. The silence of the far side is both literal and metaphorical. Literally, it is silence at radio frequencies, the absence of the electromagnetic noise that characterizes our technological civilization. Metaphorically, it represents the possibility of hearing the universe's faintest whispers without distraction, of listening to messages that have traveled across billions of light years and billions of years to reach us, messages that tell of cosmic events and conditions far beyond direct human experience. In a universe filled increasingly with human-generated signals, the far side's protected silence becomes ever more precious. A reminder that sometimes the most profound discoveries come not from adding to the noise but from finding places where we can truly listen. Standing on the far side, an astronomer would experience something no human has ever known on Earth since the invention of radio: complete silence across vast swaths of the electromagnetic spectrum. Looking up at the star-filled sky with Earth forever below the horizon, with instruments detecting only cosmic photons uncontaminated by terrestrial interference, that astronomer would be hearing the universe as it truly sounds, pure and undistorted. This is the promise of the far side, a window on the cosmos unclouded by ourselves, a place where human curiosity can reach outward unimpeded by human technology, where the questions we ask about the universe's nature and origin can be answered without our own reflection interfering with the view. The notion of the far side as humanity's radio telescope might seem prosaic compared to fantasies of alien bases or mysterious artifacts, but it represents something perhaps more profound: the recognition that the most valuable treasures are often not what we project onto the unknown, but what the unknown actually offers when we learn to see clearly. The far side's greatest gift may not be what it contains but what it excludes: the noise, the interference, the distraction that prevents us from hearing the universe's deeper stories. In protecting and utilizing this unique environment wisely, we may unlock cosmic secrets that would otherwise remain forever hidden behind the veil of our own electromagnetic cacophony. Current plans by multiple space agencies include preliminary missions to test far-side radio astronomy concepts. Small-scale experiments deploying simple antenna systems could validate propagation models, measure the actual radio environment, and demonstrate technologies for larger future arrays. These Pathfinder missions, likely to fly within the next decade, will begin transforming the far side from a speculative scientific paradise into an actual functioning observatory, bringing us one step closer to hearing those faint cosmic whispers that have been waiting billions of years to be received. The synergy between the far side's geological mysteries and its astronomical potential creates a compelling case for sustained exploration. A single far side base could support both geological field work studying the ancient highlands and South Pole Aitken Basin, and astronomical observations taking advantage of the radio-quiet environment. Resource utilization facilities processing water ice from polar cold traps could power and support both activities. The far side thus represents not a single opportunity, but a constellation of interrelated scientific and practical opportunities that together justify the considerable cost and complexity of far-side operations. As human presence in space expands and our capabilities grow, the far side's importance as a scientific platform will likely increase. What begins with simple automated radio antennas may evolve into crude observatories, then into permanent settlements where generations of scientists live and work, studying the cosmos from a platform our ancestors could only dream about. The far side that was once the ultimate terra incognita becomes, in this vision, the ultimate terra scientifica, a place entirely dedicated to expanding human knowledge, preserved and protected for that purpose, a gift we give to our descendants and to the universe's truths waiting to be discovered. Protecting the far side's radio silence also represents an interesting ethical commitment, the decision to value knowledge over unrestricted development, to preserve a unique environment for scientific purposes, to collectively restrain our tendency to fill every available space with our artifacts and emissions. It asks us to recognize that some places are more valuable for what we don't do there than for what we might do, that sometimes the highest use of a resource is to use it minimally, carefully, with awareness that once certain unique conditions are destroyed, they cannot be recreated. The far side's silence, once broken, cannot be restored. The question before us is whether we will have the wisdom to protect it before that irreversible threshold is crossed. The relationship between the far side's geological history and its present scientific value creates a pleasing symmetry. The same catastrophic bombardment that created the heavily cratered surface we now observe also ensured that the far side would remain geologically stable for billions of years, creating a platform ideal for sensitive scientific instruments. The same tidal locking that exposed one hemisphere to Earth's view while concealing the other created the radio shielding that makes far-side astronomy possible. The universe has, in a sense, prepared the far side for its role as an observatory through 4.5 billion years of patient cosmic engineering. Our task is merely to recognize what has been provided and to use it with the respect and care its unique character deserves. The far side speaks to us in its silence, and if we listen carefully, what it tells us about the universe may be among the most important messages humanity ever receives. From the cosmic dark ages before the first stars to the faint whispers of pulsars in distant galaxies, from the detection of gravitational wave signatures at low frequencies to the possibility of discovering radio emission from exoplanet magnetospheres, the far side offers access to phenomena that would remain forever hidden without its unique shielding. In an age when new frontiers seem increasingly rare, when Earth itself has been thoroughly explored and mapped, the far side represents a frontier not of geography but of observation, a place where new windows on reality can be opened, where the universe's deepest secrets might whisper their truths to listeners patient and clever enough to hear. China's Chang'e 4 mission included a radio astronomy experiment called the Netherlands China Low Frequency Explorer, a small proof-of-concept instrument that successfully demonstrated the viability of far-side radio observations. While limited in capability, this Pathfinder experiment validated the radio-quiet environment and demonstrated operational procedures for far-side science. Its success has encouraged more ambitious proposals, suggesting that within the next 2 decades, substantial radio telescope arrays could be operating from the far side, opening a new chapter in humanity's dialogue with the cosmos. The technical challenges of far-side radio astronomy should not be minimized. Beyond the obvious problems of communication relay and power supply, there are subtler issues around data processing, antenna calibration, and interference from the observatory's own systems. Radio receivers are exquisitely sensitive. They must be, to detect signals from sources billions of light-years away, and this sensitivity means they can be affected by stray emissions from power electronics, computers, and even the thermal radiation from equipment. Designing systems that operate in the far side's extreme environment, while maintaining the radio quiet that makes the location valuable requires careful engineering and operational protocols. Data volume represents another challenge. Modern radio telescopes generate prodigious amounts of data, terabytes to petabytes per day for large interferometric arrays. Transmitting this data from the far side to Earth requires substantial bandwidth and relay capacity. Processing might need to occur partially on the lunar surface to reduce the volume requiring transmission, but this requires capable computing infrastructure in the challenging lunar environment. Solving these practical problems is essential for realizing the far side's astronomical potential. Despite these challenges, the scientific community's enthusiasm for far-side radio astronomy continues to grow. Multiple research groups have published detailed mission concepts, and space agencies have begun including far-side radio astronomy in their long-term planning documents. The convergence of renewed interest in lunar exploration driven by multiple motivations: science, resources, geopolitical prestige, commercial opportunity, with a specific scientific case for far-side radio astronomy creates conditions favorable for actually implementing these concepts in the foreseeable future. The far side's radio silence is ultimately a finite resource. As human activity in cislunar space expands, the electromagnetic environment will inevitably become more complex. Spacecraft transiting to and from the Moon, bases on the near side, relay satellites, and eventually far-side installations themselves will all generate some radio emissions. Protecting the most sensitive frequency bands and the most valuable observation sites from interference will require proactive management rather than reactive regulation. The time to establish protective frameworks is now, before activities commence that might later prove difficult to constrain. In contemplating the far side as an observatory, we confront the same fundamental tension that characterizes all exploration: the tension between knowing and preserving, between utilizing and protecting, between satisfying present needs and maintaining future options. The far side's radio silence is valuable precisely because it is pristine, but studying it requires activities that to some degree compromise that pristineness. Finding the right balance, extracting maximum scientific value while preserving the core resource that makes the location special, will require wisdom, restraint, and international cooperation. The poets and mystics who throughout history have sought places of silence for meditation and contemplation would understand the value of what the far side offers. While their silence was acoustic rather than electromagnetic, the underlying principle is the same. In quieting the foreground noise, we can perceive signals that would otherwise be lost, whether those signals come from our own inner awareness or from the cosmos at large. The far side invites us to practice a kind of cosmic meditation, to still our own radio voices long enough to hear what the universe has been saying all along, patiently waiting for listeners evolved enough to comprehend. When the first radio telescope on the far side successfully detects the signature of cosmic dawn, the epoch of reionization when the first stars ignited, or maps the radio sky at frequencies never before observed with such clarity, or discovers some completely unexpected phenomenon that existing theory cannot explain, humanity will have achieved something remarkable. We will have successfully used the unique properties of our moon to transcend the limitations imposed by our own technological civilization. We will have proven that wisdom can temper capability, that we can expand our knowledge without destroying the foundations that knowledge requires. The silence of the far side, if we protect it, will speak volumes about both the universe's nature and our own maturity as a space-faring species. The geological story of the far side, bombardment, differentiation, thermal evolution, created the stage. The astronomical story, cosmic inflation, structure formation, galaxy evolution, stellar life cycles, provides the performance. And humanity's story, curiosity, technological development, exploration, brings the audience. The far side's role as observatory connects these three narratives, making the far side not merely a place to study but a participant in the ongoing human project of understanding our cosmic context. In choosing to preserve and thoughtfully utilize this unique environment, we write the next chapter of all three stories simultaneously, demonstrating that exploration need not be exploitation, that knowledge gained carefully is more valuable than resources extracted carelessly, and that the universe rewards those who learn to listen before they speak. From the first grainy photographs captured by Luna 3 to the possibility of permanent astronomical observatories detecting the universe's faintest emissions, the far side's journey mirrors humanity's expanding capability and, hopefully, growing wisdom. What was once utterly unknown becomes mapped, understood, valued for reasons early explorers could not have anticipated. The far side that served no purpose beyond satisfying curiosity now offers practical benefits, scientific discoveries, potential resources, unique observational advantages that justify substantial investment. This transformation from mystery to resource, from curiosity to utility, characterizes the exploration process generally, and the far side exemplifies it with particular clarity. Yet even as we map every crater, analyze every rock type, measure every gravitational anomaly, deploy every antenna and instrument, some essential quality of the far side will remain unchanged. It is the place Earth cannot see, the hemisphere turned forever away from our home world, the landscape that exists for its own sake rather than for Earth's benefit. This independence from terrestrial perspective, this fundamental otherness, ensures that the far side will always retain something of mystery even as our knowledge grows complete. Perhaps this is appropriate. Perhaps some places should always remind us that the universe is not constructed for our convenience or organized around our viewpoint, that reality extends infinitely beyond our immediate experience, and that there will always be horizons beyond the horizon, mysteries beyond the solved puzzles, silences waiting to be heard by those wise enough to listen. The far side challenges us to think beyond immediate human timeframes and concerns. The water ice preserved in its polar cold traps waited billions of years for something capable of recognizing its value to emerge. The radio silence that makes it ideal for astronomy will remain ideal only if protected against the short-term pressures of unmanaged development. The geological record inscribed in its ancient highlands speaks of processes operating over timescales that dwarf human civilization. Engaging seriously with the far side requires adopting similarly expansive temporal perspectives, planning not just for next year or next decade but for centuries and millennia of human presence in space. Are we capable of such foresight? The far side will test whether we can think and act as custodians of resources whose full value may only be realized by generations yet unborn, whether we can restrain present appetites in service of future knowledge, whether we can be wise as well as clever. The far side is ultimately a mirror, though one that reflects not visible light but human nature. What we do there, how we explore it, what we preserve, what we exploit, how we balance competing interests, will reveal much about our capabilities and character as a civilization. Will we treat it with respect or simply as another resource to consume? Will we cooperate internationally or compete destructively? Will we protect unique environments, or allow them to be degraded by thoughtless development? The far side silence invites these questions even as it waits patiently for our answers, written not in words but in our actions across the coming decades and centuries. Philosophical conclusion: the meaning of the hidden face. 4.5 billion years ago, in the chaotic aftermath of planetary formation, a Mars-sized object designated Theia struck the young Earth in a cataclysmic collision that vaporized rock, melted both bodies, and ejected a disk of debris into orbit. From this disk, our moon coalesced, a world born in violence, sculpted by catastrophe, destined by the laws of physics to show one eternal face toward its parent planet and to hide the other face forever from terrestrial view. For the vast majority of the moon's existence, this hidden face remained not merely unseen but fundamentally unseeable. No technique, no technology, no cleverness could reveal what lay beyond the limb, locked eternally away by tidal forces and celestial mechanics. The far side existed in a state of absolute mystery, known to exist. The mathematics demanded it, but utterly inaccessible to observation. It represented the purest form of the unknown, not merely undiscovered but categorically beyond discovery for any observer confined to Earth's surface. This situation pertained for 99.998% of the Moon's history. If we compress the entire span of lunar existence into a single year, the first observations of the far side occurred at 11:57 p.m. on December 31st, mere minutes before midnight. For all the months before, through all the seasons of lunar existence, through the formation of its crust and the excavation of its great basins, through the bombardment that pocked its surface and the volcanic episodes that resurfaced vast regions of the near side, through the entire evolution of life on Earth from simple cells to complex ecosystems to intelligent tool users, through all of this, the far side remained hidden. known to no consciousness anywhere in the universe. Then, in October 1959, a small Soviet spacecraft coasting around the moon activated its cameras and captured light reflected from that hidden surface. The photons that struck Luna 3's film had bounced off rock that no photon collected by any eye or instrument on Earth had ever touched. In that moment, the far side transitioned from unknowable to known, from mystery to geography, from absolute absence in human knowledge to presence, however imperfect and incomplete. What we discovered there was simultaneously exactly what we might have expected and subtly, importantly different. The far side is recognizably lunar, rock and crater, highland and rare lowland, formed of the same materials and by the same processes as the near side. No alien bases, no hollow interior, no exotic crystal formations, none of the wilder speculations proved true. And yet, in its details, the scarcity of volcanic maria, the thickness of its ancient crust, the enormous South Poatcan basin excavated deep into its interior, the deposits of water ice locked in perpetual darkness, the radio silence that makes it unique in the inner solar system, the far side revealed itself as distinct, different in ways that illuminate lunar history and offer opportunities for science and exploration available nowhere else. The story of the far side is fundamentally a story about the expansion of human knowledge and capability. It demonstrates that what seems permanently beyond reach may become accessible given sufficient technological advancement and intellectual effort. It reminds us that categories like unknowable are provisional, dependent on our current limitations rather than on the nature of reality itself. The far side that was categorically unknowable to Galileo, to Newton, to Einstein became knowable to Korolev's engineers and to the thousands of scientists and technicians who designed, built, launched, and operated the spacecraft that finally revealed it. This expansion of knowledge required not just individual genius but collective effort across nations, generations, and disciplines. It required physics and mathematics to understand orbital mechanics, chemistry and metallurgy to build spacecraft, electronics to process and transmit images, political will to fund expensive programs, and human courage to take risks in pursuit of knowledge. The far side was revealed not by a lone explorer but by industrial civilization mobilizing its resources toward a goal chosen for its symbolic and scientific value rather than immediate practical return. This speaks to something profound about human nature. We are creatures who sometimes pursue knowledge for its own sake, who find value in understanding even when understanding brings no obvious advantage, who cannot rest while mysteries remain within our expanding reach. The far side also teaches humility. Its surface preserves a record of cosmic violence stretching back billions of years, documenting the chaotic early solar system when impacts were common and planetary surfaces were remade repeatedly. This record dwarfs human timescales, rendering our entire species' existence into a brief flicker against cosmic duration. The ancient highlands of the far side are older than any rock accessible on Earth's surface, older than the continents, older than the atmosphere we breathe, older than life itself in any but its most primitive forms. Standing on that ancient surface, as a handful of robotic probes have, as human explorers someday will, one stands on ground that has remained essentially unchanged longer than multicellular life has existed, longer than photosynthesis has oxygenated our atmosphere, longer than any biological structure we can point to and say, "This has always been." Yet the far side also represents possibility and potential. The water ice locked in its polar cold traps could support human outposts, enable propellant production, facilitate exploration deeper into the solar system. The radio silence of its eternal earthward horizon could permit astronomical observations impossible anywhere else in the inner solar system, potentially revealing cosmic secrets about the universe's earliest moments. The ancient rocks of its highlands and the exotic materials excavated from depth by the South Poatcan impact offer scientific insights into planetary formation and evolution unavailable elsewhere. The far side is not merely a museum of the past but a resource for the future, not just history but opportunity. This duality, past and future, history and potential, achieved knowledge and remaining mystery, characterizes the far side's deeper meaning. It is simultaneously the answer to one of humanity's oldest questions, what lies on the other side of the moon, and the source of countless new questions about lunar history, planetary science, cosmology, and our own relationship with the cosmic environment. Each answer we uncover reveals new layers of complexity, new aspects we hadn't previously known to ask about. Consider the question of the hemispheric dichotomy, why the far side has so few Maria compared to the near side. We now understand this involves crustal thickness, thermal history, the distribution of radioactive heat sources, the timing and location of large impacts, and possibly the influence of Earth's presence on the Moon's early evolution. This represents genuine understanding, a major advance over the pre-space age ignorance about far-side conditions. Yet this understanding raises further questions. Exactly how did the crustal thickness asymmetry arise? What role did the giant impact that formed the Moon play in creating initial asymmetries? How did early thermal evolution proceed, and what processes concentrated KREP on the near side? Each answer spawns new questions, each solution reveals new puzzles. This is characteristic of scientific progress generally. The map of knowledge expands, but so does the border between known and unknown, and that border is where the most interesting questions live. The far side exemplifies this dynamic with particular clarity. It was entirely on the unknown side of the border for the vast majority of human history. Now much of it has crossed into the known realm. We have maps, composition measurements, age constraints, photographs at multiple resolutions. Yet our expanding knowledge has also revealed how much we still don't understand, how many detailed questions remain unanswered, how much potential scientific value remains to be extracted. The ethical and practical questions surrounding far-side exploration also reflect deeper tensions in human relationship with nature and with frontiers generally. Should the far side be preserved in its natural state as much as possible, protected as a scientific preserve analogous to Antarctica? Or should it be developed, utilized, mined for resources that could enable further expansion into space? How do we balance the interests of current populations against the interests of future generations who might value the far side differently? Who decides how the far side is used, and by what authority? These questions have no simple answers, and the far side's unique characteristics, its radio silence, its ancient surface, its ice deposits, its sheer remoteness, make them particularly acute. International space law, codified primarily in the Outer Space Treaty of 1967, declares that outer space, including the Moon, is the province of all mankind, and that celestial bodies cannot be subject to national appropriation. This framework was developed in an era when lunar exploration was exclusively governmental and primarily symbolic. As commercial space activities expand and multiple nations develop lunar capabilities, questions about resource utilization, territorial claims, and environmental protection become increasingly pressing. The far side, precisely because it has been less accessible and less explored, offers an opportunity to develop governance frameworks proactively rather than reactively, to decide how we want to approach lunar development before entrenched interests make changes difficult. Some argue that the far side's radio-quiet environment should be protected by international agreement, designated as a scientific preserve where radio emissions are prohibited or strictly limited. This would preserve its unique value for radio astronomy but would also restrict certain types of development and commercial activity. Others contend that such restrictions are premature, that we should not limit future options before we fully understand what resources exist or what opportunities might emerge. Finding middle ground, perhaps through geographic zoning that protects the most sensitive areas while allowing development in others, will require diplomatic skill and genuine international cooperation. The far side thus becomes a test case for humanity's ability to manage shared resources wisely, to think beyond narrow national interests toward collective benefit, to balance present needs against future possibilities. Our success or failure in this endeavor will speak volumes about our readiness for the challenges that await as space activities expand and the resources and territories at stake grow ever larger. If we cannot cooperatively manage a region of the Moon, how will we handle resource claims in the asteroid belt, or territorial disputes over particularly valuable orbital positions, or the far more complex questions that will arise if we ever establish self-sustaining off-world settlements? On a more personal, experiential level, the far side invites contemplation of perspective and viewpoint. Every human who has ever lived, with the exception of the 24 Apollo astronauts who orbited the Moon, has only ever seen one side of our satellite. The Moon that hangs in our night sky, that has inspired our poetry and myths and calendars, that has been worshipped as a deity and studied as a scientific object, is only half the story. There exists another moon, literally the other half of the same body, that terrestrial observers never see and never can see without leaving Earth entirely. This is a peculiar kind of incompleteness in human experience. We think we know the moon because we see it regularly, because it's familiar, because its phases and motions are predictable. Yet we're actually acquainted with only one hemisphere, and our knowledge is fundamentally incomplete regardless of how carefully we study the visible side. This serves as metaphor for human knowledge generally. We tend to mistake familiarity for completeness, to assume that what we can observe from our particular vantage point is all there is, to forget that our perspective is necessarily limited and partial. The far side reminds us that there are always aspects of reality hidden from our immediate view, accessible only by changing our position, by transcending our original standpoint. This is true physically. You must leave Earth to see the far side, and it's true intellectually and culturally as well. Our assumptions, our frameworks for understanding, our cultural narratives are all analogous to the near side. They're what we can see from where we stand. But reality extends beyond these familiar territories, and accessing that larger reality requires effort, requires willingness to shift perspective, requires recognition that our viewpoint is not universal. The astronauts who saw the far side with their own eyes described the experience as profound, though they struggled to articulate exactly why. Jim Lovell called it essentially gray, no color, sort of a whitish gray, but the contrast of the mare and the highlands was not as evident as on the front side. Bill Anders, viewing the far side from Apollo 8, remarked on its heavily cratered nature and lack of distinctive features. Yet beyond these prosaic descriptions, there seems to have been an emotional or philosophical impact from seeing what had never been seen, from looking at landscape that no earthly horizon had ever framed. Perhaps part of the impact comes from the recognition of Earth's absence. On the near side, Earth hangs in the sky, a large, blue-white marble showing continents and clouds, bright against the black, changing phase opposite to the moon's phase but otherwise fixed in the lunar sky. On the far side, Earth never rises. The sky holds only stars and planets and sun, nothing to suggest that a world of oceans and life and human civilization exists just beyond the horizon. It would be possible, standing on the far side, to forget Earth entirely, to imagine yourself on an independent world rather than a satellite, to experience genuine alienation from human context. This earthless perspective might be psychologically valuable. So much of human thought and feeling is geocentric, tied to Earth's specific conditions and our specific evolutionary history. We think about atmospheres because we breathe one, about liquid water because we drink it, about moderate temperatures because our biochemistry requires them. We measure distances in terms of Earth distances, masses in terms of Earth masses, compositions relative to Earth's composition. Our entire framework for understanding worlds is Earth-centric, which is natural and inevitable but also limiting. On the far side, without Earth in view, one might begin to think more truly cosmically, to understand the moon on its own terms rather than always in reference to Earth, to recognize that our home planet, however precious to us, is just another world from the universe's perspective, not the center, not the measure, not the reference point, but merely one planet among billions. One example of rocky world evolution among countless others. This shift in perspective, from geocentric to truly cosmic, may be among the far side's most valuable gifts to human consciousness. The far side also embodies a kind of cosmic patience. For billions of years it has existed, changed slowly through impact and space weathering, accumulated its record of bombardment, preserved its ancient surfaces, all without any observer to notice or care. The universe requires no audience. It proceeds according to physical law regardless of whether any consciousness exists to witness or understand. The far side existed in pristine indifference for the vast majority of cosmic history, either concealing itself deliberately nor revealing itself willingly, simply being what physics and circumstance made it. Then consciousness evolved, on Earth, by chance, through contingent processes that might easily have gone differently. That consciousness eventually developed technology capable of escaping Earth's gravity well, of sending instruments to other worlds, of revealing what had been hidden. In some sense, at that moment the universe became aware of the far side through human eyes and instruments. What had been merely objective reality, existing without being known, entered the domain of knowledge, became part of the universe's self-awareness mediated through human understanding. This is not mysticism but a straightforward observation. Consciousness is part of the universe, and conscious knowledge of the universe is the universe knowing itself. The far side's transition from unknown to known is therefore significant not just for humans but for the cosmos. It represents the universe's domain of self-knowledge expanding. Whether similar processes of knowledge emergence are occurring elsewhere in the cosmos, whether other consciousnesses on other worlds are mapping their environments and expanding their understanding, remains unknown, but the principle is the same. The universe, through whatever conscious beings evolve within it, progressively knows itself more completely. The far side story is not finished. We have only begun to explore it in detail, have only scratched its surface literally and figuratively. No human has yet set foot there. No comprehensive geological survey has been completed. The South Poatcan Basin's interior remains largely unsampled. The detailed distribution of water ice and polar cold traps is poorly constrained. The radio-quiet environment has barely been utilized for astronomy. Dozens of specific craters and features identified in orbital imagery have never been examined up close. There remains immense scientific value to be extracted through future missions. Within the coming decades, humans will likely walk on the far side. China has announced intentions to pursue crewed far-side missions. NASA's Artemis program, while focused initially on near-side polar regions, has far-side exploration as a longer-term goal. Other space agencies and potentially private entities have expressed interest. The footprints of Armstrong and Aldrin on the near side will eventually be joined by footprints on the far side, and a new generation of explorers will have the privilege of walking where no one has walked, of seeing with their own eyes what has only recently become seeable at all. These future explorers will face challenges their near-side predecessors did not. Communication requires relay infrastructure. Landing sites must be chosen carefully to balance scientific value against operational risk, with the heavily cratered highlands presenting more hazards than the smooth Maria that Apollo targeted. Resources like water ice, while valuable, lie in permanently shadowed regions requiring operations in darkness and extreme cold. Every aspect of far-side exploration is somewhat harder, somewhat more risky, somewhat more expensive than comparable near-side operations. Yet difficulty has never been a barrier to human exploration when the goal seems worthwhile. The far side will be explored, sampled, studied, and eventually settled not because it is easy but because it offers value, scientific value certainly, possibly economic value, definitely symbolic value as a frontier transcended and a mystery solved. The progression from complete ignorance to detailed knowledge to human presence will continue, driven by the same curiosity and ambition that has characterized human exploration throughout our history. As this progression continues, we would do well to remember what the far side teaches about knowledge and humility. Every major question we have answered has revealed new layers of complexity. Every mystery solved has opened doors to new mysteries. The map of what we know has expanded dramatically, but so has our awareness of how much remains unknown. This is not discouraging, it is the nature of knowledge. Understanding that the process is endless, that there will always be more to learn, should inform our approach to far-side exploration with appropriate humility and long-term perspective. The far side of the moon is ultimately neither dark nor light, either inhabited nor empty, either treasure nor wasteland. It is rock, shaped by physics, marked by time, waiting indifferently to be known or unknown. What it means to us, what meanings we find or impose, reflects our own nature more than the moon's. In choosing to explore it carefully and thoughtfully, in seeking to understand it on its own terms rather than merely exploit it for immediate gain, in preserving its unique characteristics while extracting its scientific and practical value, we write a chapter of our own story as much as we read the ancient story written in lunar stone. 4.5 billion years of cosmic history brought the far side to its present state. 66 years of human exploration have begun to reveal it. The next century will determine how we engage with this unique region of the moon, whether wisely or carelessly, whether with foresight or short-sightedness, whether respecting what cannot be replaced or squandering opportunities through thoughtless development. The far side, patient as always, will respond to our choices neither judging nor caring, simply being what it is and becoming what our actions make it. The hidden face is hidden no longer, yet it retains its mysteries. What lies on the far side of the moon is now known in outline but not in complete detail, mapped but not comprehensively explored, understood in principle but not in all particulars. It is a world of ancient rock and recent discovery, of cosmic violence recorded and cosmic silence preserved, of scientific value realized and potential still waiting. It is our moon's other half, forever turned away from Earth but no longer turned away from human knowledge. And in learning what lies there, we learn not just about the moon but about the universe, about ourselves, about the magnificent improbability of consciousness arising in cosmos enough to ask such questions and clever enough to answer them. The story continues, written in footprints not yet made, discoveries not yet achieved, technologies not yet invented. The far side awaits, as it has awaited for eternity, the silent patient companion of our restless Earth, ready to reveal its secrets to those bold enough to journey there and wise enough to listen carefully to what the ancient stones can tell.